Okay, so this is almost 4 or 5 or whatever it is your hour. And we have 20 participants out of almost 40 registered, which is a normal show up rate for any kind of event, I suppose. So hello, everyone. Thank you for coming. Thank you for joining for our fourth sort of annual TVS Software Workshop, which is sort of not very official event to get together and to exchange updates on our software projects, in-kind contributions, IDAC software development, and all the such. So the focus of this workshop this year is the upcoming first OSST data releases. And just to remind you, I suppose that all of you already remember this by heart, but still, just to remind you, here we are in our timeline. I hope you can see my screen. So we are expecting to have the first data preview release that is obtained from the ComCam data observations that took place on the end of the 2024. We are expecting to have this data in the beginning of summer, so probably like 3 or 4 months from now in June or July. And we are expecting to get start obtaining the first alerts from the brokers sometime probably in autumn or maybe in winter. And I suppose our speakers who will talk about the broker alerts, they will give us more information on what are their plans specifically. And our first data preview release is going to contain images and some object catalogs data, and probably maybe like a far-stretched goal, there might be some different images and forced source catalogs, but it is very much not decided. So the focus of this meeting, the focus of this workshop is what we are going to do with this data, what is our early science goals, and what kind of software we are still missing in order to maximize the return from these first data sets, which is important not only for the sake of what kind of science we can do with this first data, but also what kind of feedback we can provide to the Rubin Observatory in relation to how we want to organize the follow-up observations, what is the best cadence for different science cases, what are the optimum strategies to optimize the return for different science cases jointly, and such. So to discuss these subjects, we are having today's meeting, which will be split in several sessions. So the first session, after some considerations, it is both sessions are mix of talks on in-kind contributions and other projects. So the first session will be mostly in-kind contributions. The second session that will be after a coffee break that will take place probably in 1 hour and a half. We will have some more talks about in-kind contributions, brokers, and IDACs. And then we will have roughly 3 sub sessions, discussion sessions, discussing 3 topics that were kind of condensed out of suggestions that you sent through the registration forms. So this is our plan for today. And with this, once again, thank you for showing up. And I think we can switch to the first speaker of today, Sara Bonita. I hope that you are prepared to be the first one and have the inaugural talk. And this is it. Sarah, the floor is yours.
Thank you, Alex. So I can share the screen.
And it is, yes.
Okay, it seems
you are sort of quiet. Can you move the microphone a little bit?
Yeah, sure. Can you hear me now?
Yeah, much better. Thank you.
Okay, can you see my slide in presentation mode? Okay. So, sorry. Okay, the in-kind contribution I'm presenting today is on software development to classify variable stars with an application on young stellar objects, which is my field of interest. I'm based at the Observatory of Palermo in Italy, and this is one of the in-kind contribution by the Italian National Institute for Astrophysics, INAF, with the Transient Variable Star Science collaboration as a recipient. Here I'll show you some information on the content of the in-kind contribution, which is focused on the classification of stellar variability to help TVS members and the community or Rubin LSST in general, also through the use of the Rubin Science platform, providing also expertise based mainly in the young stellar object variability phenomena, focusing on accretion, ejection, in the framework more general of classification stellar variability, with an intensively use of analysis of light curves and color magnitude diagrams for the analysis. We are in the phase now of developing some notebooks in Python to achieve this goal. TVS is the natural recipient for this in-kind contribution, but there is also some cross-correlation with other science collaboration, in particular with stars, Milky Way, and local volume. Many subgroups and task forces of TVS are involved, non-degenerative variables, which includes also the variability of many different variable stars, including young stars, classification, visualization, characterization, crowd-free photometry. These are all task forces and subgroups of TVS, and also the use of data preview 0, and there is a dedicated task force focused on that in the last years. It is a deductible in-kind contribution for the software development in INAF. The in-kind team consists of Teresa Giannini of the Observatory of Rome, Loredana Presinsano, Mario Guarcello of the Observatory of Palermo, Alessio Garatti of the Observatory of Capodimonte in Naples, and myself. And there are additional collaborators in INAF and at the University of Palermo. Alessandro Tramuto, which is a PhD student at the University of Palermo and INAF. Sabino Stamujic, which is a postdoc, a researcher at the Observatory of Palermo, and she's also in charge of the visualization and characterization subgroup of TVS with Sally McFarlane. Costanza Giroffi and Marco Miceli of the University of Palermo, and Chiara Virzi, which is an undergrad student that joined the team, with also international collaborators, Laura Venuti in the US, in the SETI Institute, and Pat Artigan at Rice University in Houston, Texas. And okay, my last slide. We are in the phase of working to start our in-kind project, which is not yet founded. It should start next year. And in the meantime, we are working on both short-term and long-term variability, using as a starting point our field of interest, which is young stars. And so for the short-term variability, I hope you can see also my cursor here. We have recently published the Bonito and Venuti and collaborators EPJ special issue focused on the optimization of the survey cadence of Rubin LSST for the investigation of short-term variability of accretion bars. This is an example of a barster. And we have compared the main field on the left here with a specific metric for star-forming regions, for which we can obtain with a dense cadence a proper description of the light curve of an accretion burst. Here we can investigate also the long-term variability of XORI, accretion bursts in eruptive star. And the team, Teresa Giannini in particular from the Observatory of Rome, is involved in this work here by Strafella et al. And there is also Usamujic et al. In preparation to explore intermediate time variability. And Alessandro is now working in preparation of two papers focusing on DECAM data in collaboration also with Pat Artigan of the Carina Nebula, for which it is possible also to perform time series photometric analysis. This is it, because we are not yet funded, as I was saying, and we will continue developing this in preparation of the in-kind project that should start next year. And I stop here. And thank you.
Thank you, Sarah. So, questions? Okay, I have a question. So, first of all, it seems like, so at least the examples that you showed in your presentations, these young stellar objects, they present light curves that are highly irregular, so sporadic bursts and so on. Do you think how long since the start of the operations of OSST do you need in order to be able to start detecting these objects considering the OSST cadence?
Yes, thank you for this question, Alex. The early data will be important, even if the early signs won't be at the very dense cadence that we hope will be performed also at the later stage with a proper cadence for short-term variability. But in the meantime, having data also at different filters will be important for star-forming region and young stars to explore intermediate time variability. Because these objects, I don't have the time in 5 minutes, but these objects, as you are highlighting, show different behaviors. So we can explore very short time scale variability of the order of hours to days, up to the whole duration of the survey of the 10 years, because the XOR, the eruptive burst, lasts for months. So every time scales intermediate can be very important to start in the study of these objects. Of course, the ideal one is a very dense cadence of in the same filter many visits in a few days. But it is important for us also to have color information and the variability in different filters, and it's crucial also to have the long-term variability to start with the follow-up, the spectroscopic follow-up. We are involved also in different team of spectroscopic survey, like FORMOST, WEAVE, and in preparation for future instruments like Wildfield Spectroscopic Telescope, WST. So all the time scales can be explored, and Rubin LSST would be ideal for doing that.
Okay, thank you. Tobias, do you have a question?
Yeah, thank you for your talk. This was great. Maybe you mentioned this, but I was wondering if your classification methods are going to be extended to other variable stars, or will it always be for young stellar objects specifically?
Thank you, Tobias, for this question. Yes, this I have shown you here because we are not yet funded how we are going to prepare for that. And our expertise is now focusing on young stellar objects and star-forming regions. But we have the endorsement of transient variable stars for an application for different stellar variability. We already use our metrics and our starting point of investigation, considering as an example short-term variability for different science cases, like young stellar objects, but also RR Lyrae, And sometimes we also have used tools for development of metrics that can be used and has been used for Blazors. So the short answer is yes, it will be classification for other types of variable stars.
Awesome, thank you.
Thank you.
Sarah, and another question. So what kind of numbers do you expect in terms of like what kind of how many objects of interest do you expect to find in, let's say, first year of all SST data? If we are talking about young stellar objects of different types, is it hundreds, thousands, millions?
I don't have the number right now here, but if many different star forming region will be covered during the first year, even if it's not the short-term cadence, but the main survey, the Wi-Fi deep, many different star forming regions will be detected in the main survey, and all of them potentially will have members that will show variability, like accretion that I showed, but also occultation of disks. So potentially all the young members of the clusters, of course, will show the variability that we want to investigate only for the young stellar objects. If you add to this all the variable stars, for which, of course, I'm not an expert, we expect to have a big set of data. I have showed you before the I don't know whether I can show it again, but in any case, you have this. I will pass you the slides. In the Carina Nebula that Alessandro is working on, with the DECAM data in the same filters, we will have many good candidates to study variability only in one star forming region. So
Yeah, I'm just wondering what is the main like computational and software demand for this kind of science? Because if you have, let's say, hundreds or even thousands of objects, then we are talking about more or less like manual analysis, looking at them with your eye and doing like precise modeling perhaps of light curves. If we are talking about hundreds of thousands and millions of objects, that we are talking about something like machine learning, big scale analysis. So what do you think is your case?
Yeah, no, I think that machine learning will be our a must for the analysis of this kind of data set that we will expect to have in this contest. Yes.
Okay. Okay, thank you. I think we will continue on this during the discussion session. And for now, we are moving to the second talk. Tamas.
I'm here. Hello.
I think it's your turn.
Yeah, my turn. Just a second, I will share my screen and I'm sharing. And is it working?
Yep, we see it and we
Thank
hear
you very much. So my 10-minute talk is now starting. So welcome everybody. My name is Tamás Sklenár. I'm from Hungary and I'm working with Robert Szabó, Attila Bony and Gábor Kovács in the Hungarian in-kind contribution in the Konkoly Observatory. And our main focus is the classification of variable stars. And for years, we worked out some solutions in this field which utilized machine learning methods. And I will just wrap up my presentation, what I wrote in this slide. So I will talk about our machine learning based classification of variable stars, mainly pulsating and eclipsing variable stars. I will talk about some ZTF/LSST measurements just to see how well our methods will work in different data releases. I will talk about period calculations and some cross-matching projects. So let's start. So as you know, LSST will utilize 6 different filters from the Sloan filters, and we expect that we will have less data points what, for example, the Zwicky transient facility is producing. So we will have very few data points, and okay, we will have 6 different filters, but we will need long observational windows to have usable light curves for our variable stars. And of course, because it is a ground-based telescope, we will expect some noise, but it's not so huge. Just for comparison, I put here 3 different light curves. The first one is the Ogle Sky Survey, the second one is from ZTF, and the third one is from TESS. And between the red lines, you can see there is this stars light curve from TESS, which is a classical Cepheid, which has a quite short period actually. And you can see that the light curve is absolutely continuous in TESS, but in ZTF and in Ogle, there are huge gaps between the measurement points, and it's very noisy compared to space-based observatories. So this is a huge problem by variable star observation and classification. So we have to work out some kind of problem. So this is why we phase-fold light curves to have distinct shapes for different variable stars. And our institute is famous in the work of related to RR-Lyrae stars, but of course we are working with Cepheids, type 2 Cepheids, Delta Scutis, and many more. To be able to phase-fold the light curves, we need the periods, and I think this will be again the main topic, for example, in this workshop as well, because we will have no periods by the LSST, and we have to figure out something to have this numerical data by classifications. So if we have these phase-folded light curves, we can use some kind of classification method for it, and for years we switched to image-based classifications. And to be able to see what can we do with machine learning methods by LSST in the future, we used mainly ZTF data, and by ZTF we used 2 filters, G and R, and we could not use I filters because they mostly are not public. So we use these 2 filters, and from previous experiences, we developed a machine learning method. We built a very unique neural network which uses G and R filters as phase-folded light curves, and as additional numerical parameter, it is using periods of the variable stars, and we can predict the class of the variable star with this neural network. The results are very promising by this algorithm. So by some stars, it is absolutely almost perfect. And we are writing a paper now with Robert Szabo, the director of our institute, and it will be submitted in a couple of days. You can see just 5 different variable star types here, but it is very promising, but we are trying to improve our methods further. And to be able to improve our methods, we need a couple of other things. So by LSST, we wanted to know what to expect in different data releases. So some way we made different data releases by our own. So we made period calculations for 1 year, 2 years, 3 year, and etc. Observational windows, just to be able to see how well can we calculate the periods, how well can we generate light curves. And by ZTF, I think we can say that after 2, but mainly 3 years, we can work with almost all types of variable stars. We expect that it will be much worse by LSST, but we are optimistic that we can figure it out something else. So we are working on different period calculation methods. We have some theories. We just have to work it out, and we will start this work in a couple of weeks, because we have a new member in our team, and he is mainly focused on his PhD now. So when he is finishing, he can move to this topic full time. The other interesting thing is that the LSST Sky survey is a huge survey and very deep, as you know, and cross-matching targets with LSST mainly are old known targets, is very huge task, and this is why we started to collect data from different sky surveys, space telescope, etc., just to have a large data set. And I will talk about this now. So we have a bunch of stars from OGLE 4, almost 1 million, and we cross-matched these stars with Gaia, with TESS, with SSSN, with ZTF, and many more. And oh, sorry, I messed up something here. And this is interesting and very important for us, because when the LSST project will produce its real first data release, we expect that by this cross-matching table, we will already know where our targets are. And you see that we don't use just nearest neighbor method. We try to figure out some kind of weighted probability search to find our targets. And Tim Naylor will have a talk about much more detailed cross-matching projects, but he and Tom Wilson gave us huge help with this project. And the main goal of this cross-matching project is that we will already know by the real start of LSST where our targets are. And this is important because, as we know, LSST will be already cross-matched with Gaia DR3 in the start. And the idea is that at the first data release, we will already have 1 million target with its known name, no ID, and we can start to work with 6 different filters and see how well our methods are working. And maybe we can produce something like this, which this figure is from a previous paper from 2022, where we classified 16 different types of variable star subtypes with machine learning methods, and hopefully such kind of thing will work by LSST as well. So these are our projects and these are our ideas now. Something is already ready, some things are under construction, but yeah, thank you for your attention.
Thank you, Tamas. It sounds very promising and the results look very good. So who has questions first? Okay, I will start. So I have a bunch of questions. The first one is those new period determination algorithms that you are testing. Can you tell a little bit more what are they and for which science cases do you prefer to use them? that you needed to utilize them against using some more traditional stuff that is already introduced in AstroPy and so on? So what
I,
is
men-
also-
yeah,
Mhm.
I mentioned these period calculations because they are important. We always talk about period calculations, and honestly, we did not start this project yet.
Mhm.
But from other papers, we see or we expect that those methods, what we used in the past, for example, Lomskargel or etc., will not precisely work with the very scarce data of LSST. And we try to utilize all 6 filters together to be able just to see if it's working or not. Because just utilizing one filter, for example R, we will have probably 20, or be very optimistic, 40, 50 data points per year. And that is not too much, not too many. And we are trying to skip this problem by utilizing all 6 filters. We are working on some kind of autocorrelation methods, autocorrelation algorithms, but this is all, we are in the beginning of this problem. So this is what I only can talk about. Yeah.
It just feels to me like a lot of people will be interested in this kind of project. So I think this is something that we definitely should discuss at the discussion session. Maybe there is some possibility of, like pooling resources and making it a TVS-wide project, if you would be interested. Because I guess a lot of people will be concerned with this. Yes, Tomislav, go on.
I think I know what Tomislav wants to say.
I think I know too, but
Yeah, we already discussed this about the period determination in La Palma. So as I see, I mean, the main problem probably will be, okay, you can calculate with different methods the periods, but how will you use those results? Because usually different methods are more applicable for one type of variable stars. Some of them, like, I don't know, eclipsing binaries are notorious that some of the methods don't work, like Lomskargel, and you should use something else. So okay, you can calculate it a whole bunch of periods with different methods, and then what to do with that? Do you have any idea? And
okay, was this the question?
yeah, yes, more or less, or
yeah.
comment.
Yeah. Yeah, this is a good question. I think this is why we would like to experiment by the first real data release. How well can we use LSST for such kind of projects? Because let's be honest, LSST is a very ambitious project, but it's not a variable star observing project. And it will have very few data points. It can see very faint targets, but we will have just a few data points. And for us, it's concerning that we will have millions of sources below 23 magnitudes, but what to do with them. And this is why we try to figure out something. And mainly we started to talk about, for example, the period calculations in the institute, because after many workshops and meetings and etc., everybody was just silent. What to do with the periods? Okay, just start to do something. And it is not the main goal of our in-kind contribution, because our main task in the Hungarian in-kind contribution is the classification of variable stars, but we cannot do anything without the periods, so we have to do something.
Well, as a side note, I would say that probably after calculating many different periods with different methods for the same light curves, it is reasonable to produce the folded light curves and then feed them to some kind of classifier and see whether any classifier recognizes one of the periods for this light curve to be this specific type of the object. I mean, it's for some light curves that are sort of more or less high quality, not like 10 points, but something more. It's probably the only way to do this en masse, apart from like looking at the light curves one by one, right?
Yeah, it's true. Federica has a question, I think.
Yes, Pat, and then
Hi, thank you,
Hey, Pat.
Tomas. Thank you, everybody. So, Tomas, I think I heard you say that you expect your results to be much worse for LSST, and I imagine that that's because of the sparsity of the light curves compared to ZTF, right?
Yes.
However, LSST is providing additional information on the color axis. And so it strikes me that maybe, of course, I'm not in the field, so maybe there's definitely something that I'm missing, but it strikes me that really the point is that one needs to rethink what information they rely on to calculate period and figure out how to lean more heavily on the SCD for classification and for period characterization, where you find, periods in different to a lower significance because of the sparsity of the light curves, but in multiple bands. And so, LSST is not a Likert classification, like a stellar variability engine anymore than it is anything else, right? It is a survey telescope, and so we're designing it to achieve on all axes, which means we're not designing it to achieve to be optimized for one type of astrophysical phenomena. And so I think that requires a little bit of rethinking of how we extract information. So my question is this the direction in which somebody is working? Is somebody working in this direction of really aggregating color information and multi-band information?
We are trying to figure out something with multiband. This is why we started to work with multiband machine learning classification. But our problem is that now the best what we have, and very similar to LSST, is ZTF. ZTF only have 2 usable color bands, and
and I do worry a lot about our reliance generally as a community on ZTF as a precursor. There are other surveys that are, if nothing else, complementary, right? DECAM fields, for which there have been even surveys of like high densely sampled and long duration surveys from which one can extract information at the sparsity of LSST, but with more bands. And that might be a better sandbox, I think.
This is why I started this cross-mesh project to have as many variable stars as possible from different data sets in different colors as well. And just to see how our methods are working with different color information. So, for example, I did not mention, but I tried to collect data from other Sloan filter based surveys as well. But it's a huge task.
Thank you.
Thank you. Tomislav?
Sorry, I have one additional question. Did you try also to classify some more particular or more complex light curves, like semi-regular variables and maybe contact binaries? And then I have also one question. I mean, probably, as I understood, there will be no flags in the object catalog regarding the variability of the source. So did you thought about what sources will you classify, and And I mean, you have a huge catalog with a lot of sources, and how will you decide, okay, I want to classify this source and I will not classify the other one?
If I may, I will answer the second question. Yeah, this is one of my main concerns. How will I get the data? Because, and this is why I'm very open to the alert brokers as well. So the alert brokers will definitely give us alerts on transients and etc. But what about the variable stars? What about, for example, the very low amplitude stars or short period stars? So this is why I'm trying to come to this to the other side, to have about 1 million targets from the southern sky, which are already known targets from many different variable star types, and to use these light curves from LSST, how these stars are working in this sky survey. This is really, so your first question, now our methods, what we are now working on, these are very much based on the OGLA 4 catalog, which contains, for example, non-contact or contact binaries as well, from long periods variable or short period variable. So it's a very, very complex data set, and this is and very well classified data set. This is why we are relying on this one, because I think our Polish colleagues made great results with this database, and we are focusing on these stars mainly. After that, we will see how well LSST will work.
Yeah, thanks a lot. Thanks.
Yes, thank you. So a follow-up question. What is exactly the criteria for selecting the stars for this cross-match sample? Do you rely on variability classification from some survey, from Gaia or from somewhere? How do you determine which stars you are cross-matching?
No, it's painful to hear, but the classification database of Gaia is full of errors. So it has to be said out loud that I don't trust the variability catalog of Gaia, because most of the stars are misclassified. This is why I had talks with Tim Naylor or Tom Wilson in the past, because they are working on larger scale cross-match methods, and this is why I'm using also other informations as well, not just which sources are close to my targets. I'm using brightness. If the catalog what I'm cross-matching with has, for example, some kind of variability data, I'm using amplitudes, periods, etc. So I'm trying to have as many matching parameters as possible to be able to say that, okay, this is my target in Gaia DR3. And yeah.
Okay.
Yeah.
Thank you.
Thank you.
I think that once again, we are going to continue this discussion in the next sessions. And for now, we are moving to the next talk. I think this is Marcus. Marcus, please.
Hello, everyone. It's my pleasure to talk today and give an update on the Microlensing Observing Program Manager, which is one of the in-kind contributions here from our in-kind team. And this in-kind team is Yannis Tsapras and myself here at Heidelberg University. And I'll give a brief update on the status and what this in-kind contribution is about. And before moving on there, I actually go a step back and talk a little bit about the way how the in-kind procedure worked for us, and how also in the TVS Software Task Force this worked. So our contribution here is from ARI, which is one of the institutes at the Heidelberg University. It was a directable software contribution and is a directable software contribution. And the initial proposal was to deliver a target and observation manager system or instances thereof. It was initially decided to make a little detour and to add a code base for a user database, which was delivered and then gave us the opportunity to restore and to return to our original plan, the Observing Program Manager, which is then an instance of that. As early adopters here in the TVS Software Task Force, we gladly seized the opportunities to take part in the IEEE courses on requirement and design analysis at the start, also the intermediate Python courses. For those who never been here, you will find material, and I'm absolutely sure that Alex can give you more details on where to find them. Thank you so much for organizing and for providing these opportunities to us. When we've then moved on to the Observing Program Manager, we first needed to decide on where to actually test it and which subgroup. Of course, it is close to our heart. The science close to our heart makes it easier, but not only that, it's also the microlensing subgroup, which we're using currently as testbed, is already known to have an existing ecosystem of program managers, target observation managers, however you'd like to call them. And there are two things that are particularly, we've identified as particularly important. One is provenance tracking. One of the brokers is also gearing and is particularly putting an emphasis on that, the Ample team, because when finding microlensing events, it's of course not only important what we find, but also what we don't find. And so in order to make sense of what we are seeing, we need to get an idea at how events evolve, how data reductions will update, especially if alerts change over time with renewed template images. But this is, of course, something more for the future, but in more immediate of concern is, of course, the priority management. And so in the context of the last talks, I can say we are focusing not only on the classification as part of this project, but rather also how to transform and amalgamate multiple priorities, so classification probabilities of the targets of interest, and also how to handle proprietary telescope access, because some of the teams are not available are not actually having access to certain telescopes. Others have access to the RSP, some don't, and this puts us into an interesting, challenging position. So the ecosystem that exists in the microlensing community are systems where events are harvested. A database of all these events is then stored with the respective team, and it's also a sociological experiment in some sense. And these are actually then certain teams have access to observatories, different overlapping or disjoint sets of resources, and the microlensing OPM is supposed to be somewhere in the middle, getting an idea of all the events and with a different prioritization and as suggested by the microlensing subgroup, then communicate with the existing ecosystem, but also with IDAX, as we will hear about from Tomislav, for instance. So this is the basic idea. But the overlap of functionalities is actually a strength. So it's sometimes good to reinvent the wheel, because your wheel can have multiple features. It can be the Formula One car wheel, or it can be your bike wheel. So that's a good idea depending on your use case, and because groups and sociologically have organized in certain ways, this is there. We see that filters will be part of brokers, part of the Rubin Science platform will be part of observing program managers, and so on and so forth. So the demo system is reaching the beta stage where it will be delivered. So the first broker that delivers microlensing alerts, that is Fink, and thanks very much to them for also providing plugins and tools to actually harvest data. And we understand, as we've also heard in last talks, the first year will be very exciting in various sense and for various reasons. We need external data and more idea of what these events are and how the alerts what these alerts are. And so all teams are working on getting a better understanding. Here on the right side, you see a known published microlensing event and some remote data here, for instance, ingested from Atlas. So it gives us an idea that this is a microlensing event. And also on the Alerce page, just to quote another broker, we see that the alert package in red and green would have been a microlensing alert, but without the actual data release on baseline coverage, the classification would greatly differ from what we would see. So in preparing filters just for year one and then for regular operations is the challenge. And so that needs to be, of course, always every programming and all managers and observing managers will have to deal with that challenge. But it will be very exciting because we will see here really new things that we never did before. So to summarize, we're currently tests with Think microlensing events, and more filters and classifiers are in preparation. A filter for Antares, for instance. And there will be the exciting challenge to get from ZTF to Rubin alerts. Last week, we for the first time handed over all the code to our admins here at university for deployment. So to get the beta test rolling in April. So which is a great and exciting times for us, and we prepare to connect also to compute centers. And again, this will when this will emerge as soon as we understand when this is necessary, also to connect to the other ecosystem of target and observation managers available. So we are looking for a second TVS group subgroup to discuss possibilities how a second OPM demo could be implemented, and to start the discussion. And that would be all. Thank you so very much for your attention.
Thank you, Marcus. Okay, great. Questions? I guess I will start again. So perhaps you mentioned it, but I missed it. Do you plan to, maybe not plan, but would it be easy to add additional science cases into your OPM? So for example, right now it is mostly focused on microlensing events, but if, for example, would it be possible to repurpose it also for, I don't know, AGN studies, TDEs, supernovas, something like that?
Well, the idea behind it is really to have this a science case specific system. You could, of course, envisage to have one or two, but because you have multiple groups overlapping and multiple aspects, it is usually, so it is in your interest not to have a monolithic system, but rather something that you customize and where also the respective subgroup has full control of. So if the needs of a microlensing community will be very different from the variability, as we've heard. Also the scale of events when we integrate multiple of these science cases, you end up basically ingesting or replicating also the spirit behind the brokers, because you're hosting then all alerts in some way. So this is why divide and conquer here, find a suitable way to deal with these things is a meaningful approach.
Yes, I also wanted to ask, so essentially you are not ingesting the full stream of alerts from some kind of broker. You already ingest only pre-filtered ones, right?
Well, for microlensing, this would be the case. But of course, you can also define the filter stages. It depends on the broker again. Antares would let you define a filter, which gives you a pre-selection of events that are not classified reliably and evolve over time. So, which is also again something that will be we will see, and this will be very exciting to see how that evolves in the first year. But I think, given the ZTF data after year one, we will have quite a good view what kind of events there.
And do you already have any timeline of how and when you will be able to integrate LSST alerts into your OPM? So essentially, there was like this question on one of the last slides that how do we switch from ZTF to LSST? Do you already have any plans, or is it just is it not defined yet?
Well, since the system is based on the Tom Toolkit system, and thanks very much to them, it will the modules exist, and we connect actually to all brokers that are available, and so we can ingest it right away. Understanding it right away is a different question, but ingestion, hopefully as soon if we on your timeline in autumn, if everything works as planned, we will hopefully see the first events appearing in there.
Okay, I see. Thank you. So yes, Tomislav, your question.
Hi, Marcus. I just wanted to ask you, in the previous discussion, you mentioned quite a lot that you will need quads. So is this still holding? I mean, regarding the further data analysis in data centers. So will you need the quads to be accessible during your analysis, or?
So I hope the discussion part you're mentioning is the microlensing community to get to the baseline of our event may need to get for some events CoAS, but the bright ones, the one that can be followed up, probably not. But for getting a comprehensive overview, those events that are too faint to be detectable in single exposure images will of course need eventually over the next decade the refined catalog releases in order to establish their baseline magnitude. But again, the faintest ones are also the least likely to be followed up first, because observing resources will also carefully allocate it to projects.
Yeah, thanks a lot. I'm just asking this because probably just a minority of the IDACs will have access to the card. So probably the full IDAC, and everybody will go just on that one.
Yeah, again, we will not wait for 10 years in order to get an initial analysis. So the analysis of whatever is there, even with an artificial baseline, you will find that on the OGL database as well, will move on. So that there will be demand, I suppose.
Okay, thank you. Any other questions? All right, thank you, Marcus. And then we're moving to the next speaker, Tobias, please.
Hello, good morning or good evening, depending on where you are. Let me just share my screen real quick. Cool, does this work?
Yep.
All right, so hello everybody, my name is Tobias Chiron. I'm a postdoc at University of Toronto, and today I want to talk a little bit about what we've been doing here. So I know the title is like it's a lot, but basically we wanted to spend some more time trying to dig deeper into the detection thresholds that Rubin quotes. And the science context behind this is pre-supernova variability, which I'll be talking about in a bit as well. I wanted to mention that this is all still a work in progress, but I think we're most of the way there. But if anybody has any ideas or comments, please let me know. So basically, we've all seen a bunch of light curves before. This is a simulated light curve that I got from Rubin. And the question that we wanted to answer is, well, so like all these points are very clearly, can you see my mouse, by the way? I don't know if you can. Yeah. So all these points are very, very clearly detections, right? But we're not super confident about detections like this that are like swamped around other non-detections. And so the Rubin pipeline currently uses a signal to noise threshold of 5, I believe, to distinguish whether something is a detection or a non-detection. And that's what we want to solve, right? Like, can we trust these detections? One of the reasons why this is an issue is that image subtraction apparently is a hard problem. It doesn't always work as we expect, especially in cases with super bright background galaxies, right? And this is, again, an example that I got from DP0, where there's like a galaxy, and this epoch was quoted as a detection by Rubin, right? So like there's a galaxy and there's the template, and when you look at the difference, there doesn't really seem to be anything there. And then if you do force photometry on every single pixel, we basically see that the whole galaxy is flagged as a detection. So this is an issue that we wanted to address, and shows that we basically need a tool to help to better help quantify detection thresholds. And so the science context here, as I mentioned in the beginning, is pre-supernova variability, but you can use this software in any science context, right? And so basically the story for this is that the spectra and light curves for some type 2 supernova imply that the progenitor enhances episodes of enhanced mass loss. And this would manifest itself in the light curve as detections before the supernova goes off. And this is found for a few targets, such as 2020 TLF. It's also found in 2009 IP, which is the blue line here. So this is when the supernova goes off, and this is the variability prior. And so the duration and brightness of this variability helps us to understand the mass loss mechanisms and then, stellar evolution in general, because there's multiple ways we can explain this. We don't always find stellar variability, even though when we expect it, right? So this is an example, 2023 IXF. From Rest et al., which is a really cool paper, by the way. They couldn't find anything there. So the question is, did it not experience such an event? Was it too faint to see? And, we can still learn something from the upper limits. So to kind of summarize all of that, the background, understanding pre-supernova variability will better help us understand type 2 supernova in general. And so it is hard measuring these things because, we need to be confident that the detections are actually real. And this is hard because the variability is very faint and it's typically close to the detection thresholds, right? And to complicate things even further, they're typically embedded in bright nearby galaxies, which makes image subtraction hard again. So to kind of visualize the workflow that how we want to solve this is I basically created an artificial light curve, which is basically the light curve of the supernova I showed you before, but just shifted to like a distance of 130 megaparsecs, and I also added like a galaxy in there, NGC 6308. And the basic idea of our workflow is very similar to what the Young supernova experiment did before. And so typically you would run this pipeline on targets like this, but just for the purposes of today, I wanted to show you the pipeline run on this target, like on this epoch, just so that you see that actually something is there, because it's easier to visualize. Cool, right? So you have the science template, the difference, there's very clearly something there. The pipeline is as follows. First, we find locations in the template images that have similar background flux to the supernova. So here the cross is a supernova, and these rings here are different locations with similar background flux. Then we inject fake supernova at all these positions. And I don't know if you can see this actually in the image right now, but here in the original exposure, you can see the supernova here. And now in the injected exposure, there's also 3 extra dots here. Then we use the Rubin pipelines to do image subtraction and force photometry, and you can very clearly see that these new injected supernovae show up there. And then you just repeat it for a bunch of different locations at a bunch of different magnitudes, so that you can basically say the Rubin pipelines recover 100% of sources with this magnitude. And then you can finally create a curve that looks like this, and like quantify the 50% and 80% detection thresholds. So just to bring this point home, the goal is to confidently measure how sensitive the Rubin pipelines are for a very specific epoch with a very specific template, right? And so if you run the code for this epoch, for example, you'll get a recovery curve that looks like this. The vertical dashed line is the magnitude of that specific point. So now we can say, like, actually, the Rubin pipelines for this specific epoch and templates, 100% of the times will recover a source that looks like this. The goal is to make it super simple to use, right? So it's just an import statement, a config statement, and then just run this function. You input the science exposure, the template, some sources for the image subtraction, and the locations, and that's it, basically. The reason why I don't do a live demo is because at the moment it still takes a while to run. So it is it's like 3 to 4 minutes per data point, which isn't great. I've tried to optimize this as much as I can, but the limiting factor right now is the Rubin subtraction pipelines, and we can't really go around that. So, but if anybody has any ideas for that, I would be very happy to talk to them. So yeah, in conclusion, we basically wanted to build a tool that helps us quantify the detection thresholds for a very specific epoch, very specific template using the Rubin pipelines. And this is done with a series of injections, subtractions, and force photometry. And this code will eventually be made public on the Rubin Science platform. And any questions, I would be very happy to answer them.
Thank you, Thomas. So, questions?
Hello,
Yeah, please.
Hello.
So will there be individual filters, data for all the filters would be calibrated one by one, or would you just take the data points and then just do an average magnitude for a filter?
Sorry, the connection wasn't great. I don't think I understood what your question was.
Yeah, sorry. So when you're taking the data points and then you are checking the magnitude, is it going to be done for every single filter, or you just take the data points and
Yeah, I see. Good question. So you can do whatever you want. So like this is designed so that you can do it per separate filter. But if you're of course really interested in one specific data point, I think you would want to run it for every single filter. Yeah.
Yeah,
So
and
the
then
algorithm.
the magnitude
Sorry.
would be different for each filter, right? So you would
Yeah.
have different ones. Yeah.
Yeah, that's right. Yeah.
Yeah. Okay. Thank you so much. Yeah.
No worries. Thank you.
I actually have a question that is probably, I mean, I'm very far from this area, so maybe it's a bit of a dumb question, but can you use core information from the images to actually also kind of increase the threshold of detection? So obviously, okay, if you have one cutout in one filter and you have bright dot that wasn't there before, you can say that this is a supernova. But what about if you take a pair of images in different filters that are done with like little time difference? Then you make like a core image and then you compare it to a color image from a template and then see the change in color on some pixels. Can it help? No?
Yeah, maybe. I hadn't actually considered that, but that might be a good way to look at things as well. Yeah.
Okay. Okay, any other questions? Ed, yes, please.
Yeah, Alex, I think that's a really good idea, especially considering that we do take 2 exposures typically in different filters at 30 minutes interval. So I hadn't thought about that either, but that's a very good idea.
Hallelujah. Okay. And thanks, Tobias, again. And I think we can move to the next speaker, which is Eduardo. Please. Are you around?
Yes.
Oh, hallelujah. Okay, the floor is yours.
Okay, let's share the screen. 1 second. Okay, can you see the screen?
Yeah, we can see it.
Great. So hello, I'm Eduardo. I'm a PhD student at the University of Nova Gorica in Slovenia. And here we are working on, hopefully, some photometric classification methods for tidal disruption events and nuclear transients with LSST. So LSST, as we know, will discover thousands of transients every night. A lot of them, or a significant amount, will be nuclear, meaning they are located in the central regions of galaxies. Out of these, this can be there's several different types of transients that can be considered nuclear. Around between 10 and 20 are expected to be tidal disruption events, which occur when a star is disrupted by the tidal forces of the supermassive black hole. And if we look at the expected redshifts and distances, around 10 to 20% of these could qualify for follow-up observations, which doesn't seem like a lot. But if we look at the total numbers, this will be a much larger sample than is available now. So the main problem with this is that, as we said, nuclear events include other types of events, not just tidal disruption events. We can have supernovae that just happen to be in the central region or in the line of sight, AGN activity, and other more exotic and less common types of transients. So up until now, the classification has been done by simply spectroscopic observations, but with these numbers, this is simply not possible. So if we want to have, if we can have some quasi real-time classification, this would be great to fully optimize the potential of Rubin in this regard. So if we want to do this by simply taking into account the photometric information, we aim at exploiting these differences in colors and timescales, essentially. So there's been some studies that show that TDEs differ from supernovae and AGN mainly in the color and the timescale. So on the right, we can see that TDEs tend to show a bluer color. This is from ZTF data, so we're doing G minus R. TDEs show a bluer color and longer timescales in both in rise and fade than supernovae. The color also tends to be way more constant than in supernovae that with time become redder. So the idea is if we can try to exploit these differences to make a robust filtering algorithm to tell apart TDEs from supernovae and AGN activity as soon as possible. So with this in mind, we are running two parallel projects. So observationally, we've been running a project for about a year now as part of the PESTO collaboration of ESO, where we're taking in ZTF nuclear candidates, filtering them by a simple filter on the laser broker to take in these nuclear candidates and classifying as many of them as we can, of course, spectroscopically as of now. This is to get an idea of how many TDEs, how many supernovae, how many AGNs we expect to see in the central regions of galaxies. So for now, about 65 to 70% of the sample is supernova 1A, which is expected. And we see that TDEs can account for about 5 to 10% of this sample. Of course, here we need to take into account that this depends a lot on the criteria that we use for the filter, mainly on the distance to the nucleus that we can consider as nuclear, right? So for now, we're using 0.5 arc seconds, but this can be extended to larger distances, which will probably increase the diffraction of supernovae and other events. We've also found a few other more exotic events like Bowen fluorescence flares and just a few AGNs. So if we look at LSST, what we can try to do, and what we're doing now mainly with plastic and elastic data, is trying to fit a function, basically Gaussian rise and exponential decay in all the bands that will be available, so we can estimate color pairs at different times. So just subtracting, as we were doing before with ZTF G minus R, we can do other bands and get the color information. Then we can compare these parameters for different events, or for mainly right now we're comparing supernovae and supernova 1A and TDEs, and see if we can find any significant differences in the distributions that we can use to find some cutoff values where we can define, okay, this combination of values we can use to determine this could be a TDE with a certain confidence, right? So on the bottom, for example, we can see a very simple example where we're plotting the U minus I color. In blue, we see TDEs, in red, supernova, and we see there seems to be a significant difference in the distributions. Of course, this is very preliminary. This is ways easier said than done. It's one big problem that we have is, of course, we need to do this as soon as we can in the light curve to be able to classify and know what objects are worth follow-up as soon as possible. But of course, if we want to fit a function, this does not work as well when we just have a few data points. So this is something we are working on to see how early can we go. So the main idea would be to have a preliminary nuclear filter, as we're using now for our observational project, where we can just select certain nuclear candidates. Then we could do this fit to all of this, all of the events that we see, assign some probabilities with some random forest classifier, for example, and then this would go onto some broker or Sky portal where the user can see the probability we're assigning and whether something is worth following up. Another thing, of course, would be that when new data points come in, this whole process should be repeated and see what the parameters look like now. So finally, as I said, this is quite preliminary yet. We have a lot of things to think about, for example, the optimization. So we need to do this as early as possible when there is a detection, but we need enough data points for the fit to be reliable and to give us reliable information. It needs to be flexible. So when we get new information, we need to quickly be able to run the fit again and update our classification if necessary. If we get historical information, or also information, context information from the galaxy, say redshift or photometric redshift, we need to see how we can use this in a favor for a more reliable classification. Of course, collaboration with brokers and users will be critical in order to ensure the flow of alerts is smooth, and we are doing this in real time or as close to real time as possible. One idea that would also be really helpful for this would be if there's brokers that are thinking of having supernova classifiers. So a simple binary classifier that tells us if something can be a supernova or looks like something else, then we can just take whatever is this something else that is not clearly a supernova, and that would reduce the number of events, increase the proportion of real TDs that we're working with, and make for a much faster process. Of course, we also need to think about the first selection filter. We've seen recently that there's been off-nucleus TDs, 2024 TVD, for example, that was found at a much larger distance from the nucleus of the galaxy. So if we see this this algorithm is reliable, we can expand and make this initial filter way broader for a more complete samples. So we hope to, in these following months, have something ready that we can start using with the new alerts. But as I said, there's a lot to be done yet. So if anyone has any ideas or any inputs, very happy to talk about that. Thank you.
Thank you, Eduardo. So yes, right away, Kostya, questions.
Yeah, thank you. Very nice talk. Kind of, repeating the question we had before for periods estimation. Do you, when you feed light curves, do you use any correlation between passbands, or not? Because I know that in, for example, supernova analysis, there are codes like Superfort Plus or Rainbow, which apply different approaches to correlate different passbands.
No, so for now we're doing it the much simpler way. No, we're not using any correlation yet. We're taking a very simple approach yet, so far, and then slowly we can think of more complicated things. But no, so far, no.
Thank you.
Okay, thank you. A nice place.
Yes, nice talk, Eduardo. I had a question about how early do you need to disentangle this type 1a supernova or supernova in general from the TDEs? So would you be more interested in something early type 1a supernova classifier, for example, or something that uses a bigger light curve? Do you have anything about that? And my second part of the question was my think hat. I can tell you that we have been experimenting using Rainbow to do TDs multiband, and this is something that we will be more than happy to discuss whether it works for your science case or not.
Okay, thank you for the question. Yep, for the second point, yep, that's very interesting. Would be happy to talk more about that. And for the first question, so ideally we want this as early as possible. So we need to know if something is worth taking spectral images of. We need to know how important the follow-up is. So TDs tend to have a slightly longer rise time than supernovas. So, I mean, ideally in the first weeks, we need to be able to tell this thing apart, like before peak for sure. That's the main idea, right? But of course, that's not easy. But yes, as early as possible, say in the first weeks.
Okay, thank you. Tamas?
Yeah, thank you for the talk. Maybe I missed something, and sorry for that if I made a mistake. If I understand it right, you are currently trying to figure out these things with simulated artificial light curves, right?
Yes.
Did you try out your methods in real observational data?
That is the next step that we want to do. So far we're using plastic and elastic. We also have someone working with simulating TDs with MOSFET. And then also we want to try this with ZTF TDs. Of course, it will not be the same if we only have 2 bands, but the approach would be similar. So yes, that's the next step that we want to do.
Yeah, great. Thank you.
Okay, thank you. Any other questions? Nope. And then we can move to the next speaker. Tomislav, please.
Yeah, hello everybody. Just to share. Okay, I hope you see the presentation.
Yes.
Yes. Okay. So hello everybody. My name is Tomislav Jurkic. I'm coming from the Faculty of Physics at University of Rijeka. So today I would like just to give an update of the current status of our supercomputer Bura that is used as a software processing center for the Rubin related science. So we are part of the Croatian in-kind contribution of Croatian participation group that consists of Institute Ruđer Bošković with the group leader Laura Palaversa, and then also University of Zagreb, Hvar Observatory, and Faculty of Physics, University of Rijeka. So our in-kind contribution is mainly divided in 2 parts. One part is software development, which is led by the University of Zagreb and Ruđer Bošković Institute, and then the other part is the computer contribution in the form of software processing center. So we are currently mostly active in 3 science collaborations, mainly in transient and variable stars, but also in Milky Way and in solar systems. So they are all running some kind of simulations on the Bura that could be of interest to the wider community. So for if we talk about the computer resources as in-kind contribution, that you probably know that most of them are in fact IDACs, which are data access center, but also there is only one, and that's Bura, used as a software processing center. So there is quite a difference between a data access center and the software processing center. So the SPC is dedicated computer resource for CPU intensive analysis and processing, and on which the demands for CPU power are higher, and usually there is also lower disk storage. So HPC facility, the high performance computing facility, comes very nice in this framework. So what we do, what we can offer to the wider community. Mainly we offer substantial amount of CPU hours for mainly stellar time domain astrophysics, but of course we are open to all other science collaborations and to any other scientific topics. We have a collaboration with Slovenian Light IDAC in Maribor to access the data, mainly the object catalog that is important for the stellar astrophysics. We can also give and provide astrophysicists domain support to run the analysis, to run the computation. And our main aims is in fact to give opportunity to analyze both a large amount of data, but also to give opportunity for individual smaller groups for small-scale computing that usually do not have access, easy access to such a facility, to similar facilities. So it must be emphasized that our facility is not suited for development. So currently there are no Jupyter notebooks, although we have one server with Jupyter notebooks. So even if you need something like that, we can arrange it. But generally, it's not suited for development. So Bora supercomputer is a high-performance computing facility. It was in top 500, but that was quite some time ago. The peak, the air peak is around a little less than 300 teraflops per second. There are altogether 288 nodes with 24 cores per node. If you look at how the system, what is the structure of the resources at Bora? So the main part is the cluster part with the compute nodes. It has altogether a little less than 7,000 cores with 18 terabytes of total memory and 100 terabytes of total disk space available in these nodes. Then one part of the cluster is now reserved for the grid computing, so you can do array jobs. That's between 40 to 50 nodes with up to 1,200 cores, which is ideal for any calculations and simulations that use large grid of parameters. So it's like something like a pseudo parallelize computing. Then there is also the SMP nodes that has quite a large memory, 12 terabytes of total memory. So if you need a permanent access to a large amount of data at every moment, at every instance, then you can use the SMP nodes. But then the number of cores is 10 times lower than if you use the compute nodes. There is also a GPU node that one is not a big one, so it's not often used. Regarding the operating system, we use the Red Hat Linux, and for the workload manager, Slurm is used. There is a Scratch file system of 1 petabyte, but there is also a tape library that can archive 2.5 petabytes of data. So this one is a little bit slower, but still can be used for quite a lot of different tasks and different jobs. So as you can see, the amount of disk storage is quite okay. There is also disk storage extension through regional elastic cooperation grant. So at University of Kragujevac, we can provide even more disk storage if needed. So I will now just present a few of the science cases that are already running or that are possible. So what we plan to do is to host object table, which would consist of up to 75 terabytes of data and offer 2 million of CPU hours per year for LSST related computation. And what we plan to do is to host mainly a Stellar catalog that should be around 35 terabytes of data. These are the estimates for the 10 years of LSST observations. So regarding the science cases, some of the science cases that are in fact run now, there is a SORCHA, Solar System Survey Simulator, that is run by the Solar System Science Collaboration. It's a survey simulator for Rubin LSST, and they just try for different orbits to estimate the brightness of simulated solar system small bodies, and then to determine which one of them could be detected by Rubin LSST. The next one is the PhotoD, which is a method to estimate the stellar distances and metallicity, and also to provide the interstellar reddening. So it's in fact, it's a broadband photometry, which is used to estimate distance. It's run by Laura Palaversa and Željko Ivetić and Karlo Mrakovčić. Karlo is a PhD student at our university. So he's trying to use the machine learning and convolution network to speed up the process of determining the stellar distances. Then also Anđelka Kovačević, Dragan Ilić, and the group from Belgrade and from Kragujevac, they also run the periodicity mining pipeline using the Bura supercomputer. So more or less, it's a Serbian in-kind contribution to identify, classify, and to determine periods using the light curves of BBH objects. They use the two hybrid code with time series, autocorrelation, and then also machine learning for gaps. But more information you can find out in a talk by Anđelka Kovačević that will be a little bit later. Then there is also a very active calculation of nonlinear hydrodynamic pulsation models of long period variables by Michele Trabucchi. He is from Leo Girardi group at University of Padua. So what he tries to do is to simulate around 3 million AGB enveloped models, and then he tries to extract the pulsation periods and light curves, and to compare it with observations. This will be also an important part of trilegal catalogs. Trilegal catalog, which is a simulated catalog of stellar populations in our galaxy. Then with Markus Hundermark, we also talked about using the Bura in macrolensing events. That's still in preparation to detect and characterize the events across the sky. So you already had opportunity to hear his talk. Then we also had a talk with the leaders of dark energy science collaboration. So they plan to possibly use Bura to simulate the dark energy, and also in the future when we talked with Tamás and the Hungarian group, maybe it could be also a good idea to use Bura to determine the periodicity of variable stars, to use different finding techniques. Of course, but this is still in preparation. It still needs to be done. How to access Bura? Just a few words about this part. It's quite easy. So you just write to me, and if you have the data rights, we can do it. But I mean, after LSST starts to work, up to now, almost everybody who is a member of Science Collaboration can get access. So we just need the name and surname and your IP address from which you plan to access the facility. How do you access the facility? You access this through the VPN channel, and then you can use the SSH terminal and run the SLARM script or whatever you need to run the calculation. There is also possibility to use the web, but this one is not recommended because it's just not recommended. So VPN client, 40 client is used. You just made a VPN connection. It's available on different platforms, so it's easy to install. There should be no big problems. And for the SSH, there are two login nodes. You can log in and then use the SLAM workload manager to run your jobs. Of course, as I said, there is web access, but it's not so much used for some real work. Alex also, so for the takeaway, what we can say at the end is that Bura can be used for computer-intensive calculations and analysis that will require a large CPU power. And what are our challenges? Our main challenges are in fact integration of HPC as an SPC with other services, with other catalogs, with databases. Usually it's because HPC is not suited for fetching data outside of its own universe. So you cannot so easily, when you are logged in the HPC, it's not so easy to get around the internet and fetch the data outside of the HPC because of the cybersecurity. So there's also challenges regarding access to the data. do we make bulk download after the release, or use, for example, Russia software framework for data distribution? What we plan is to locally host part of the Rubin data, Stellar sources, but then there is always this question of how such catalogs will be built. Will the sources be flagged, or should we do it by ourselves and build our own catalog? Then, of course, there are always challenges of customer support, of funding, and hardware equipment getting old, but these are more technical issues. Alex also asked me to give a few words about the IDAC coordination group. As I see, Knut is around here. He is the leader of the group, so maybe he is better to explain what's going on in IDAC coordination group. I will just say that there is a dedicated channel on LSST Slack, which is now called Discovery Alliance. So if you want to know what's going on, you can always become the member of the channel. Mainly the main discussion topics at this moment are data and data transfer and authorization and access. But as we are an SPC and we are not so much involved in those two things, as the authorization at Bura will be very simple, depending from one case to another, because we don't expect to have a large number of customers. So this is maybe a better address is to talk with George Beckett and Stephen Gwynn, who will later present the UK IDAC and the Canadian IDAC. Then also there is also quite a lot of discussion with the LSDB HATS project and link framework, but you can see Konstantin Malachev talk, who will give it in just a few minutes, I think. I mean, after the break. Then maybe some other information that could be interesting for wider public is that the first data preview will probably be at earliest at June and July. This is info by Knut Olsen, so maybe he could also add to it. Some estimates of the amount of data of this data preview is around 20 terabytes for the full DP1, and then less than 1 terabyte if you will use just the object catalog. So thank you for your attention, and if you have some other questions, I will be glad to answer it.
Thank you, Tomislav. Yeah, topic of IDAC is always causing a lot of questions, and as you correctly noticed, the main questions are authorization and data transfer, and IDACs are usually like, we don't know how it's going to be done. So it's like a common place where we were all very curious and very puzzled. So any questions? Yes, Rachel, please.
Hi, Tomislav. Many thanks for that presentation.
Hello.
I just wanted to ask, notice you use the Slurm Tasks Manager, and I know there are a number of them out there on the market, and I used Slurm many years ago, but I don't have a lot of experience with it. So coming at this from a user's point of view, is there any documentation? Is there any planned workshops to help users like myself to overcome that kind of energy barrier to actually using the Bura cluster?
Yes, I mean, Bura is also part of the wider collaboration of the HPC across the Europe. So they have prepared quite a nice manual with a lot of examples on how to use, a lot of practical examples. So this manual is quite informative. Then there are also some video guidance on how to use Slurm. We can also organize a workshop on how to use it. There is also some some kind of recipes that we can offer that is just a standardized form of Slurm tasks that are usually mostly run by the people who wants to do something on the HPC. Of course, depending of if your code is parallelized, so you need the MPitch or something like that, or it's not parallelized, so you make some kind of array grid calculation. But some of these recipes are already written, and you can use it. So it's really, it's quite user friendly, I would say. There is a lot of documentation on it. So this is probably why the Center for the Computation, the Trans Bura, choose to use Slurm, because like 5 years ago there was a different workload manager, so they decided to move to Slurm. So.
Thank you. Yeah, that documentation sounds like a really great place for maybe the next TVS software workshop, is just running through some of those examples and helping everybody get familiar with Slurm.
I gave a presentation with the Dark Energy Science Collaboration. With maybe I had more time, so I presented them also some of the recipes how to use Slurm. But of course, if there is interest, we can do it in TVS. We can do it in any other science collaboration. And then if there are some specific requirements, we can always organize the workshop. And the guys that run Bura are very open also to organize some Zoom workshops and to spend a few hours with you with your specific requirements and to help you to run the code.
That would be great. Thank you.
Sounds like a good plan, and something that we probably should discuss at the next software regular meeting. Maybe plan something for later this year. So thank you, Rachel, for raising this point, and thank you, Tomislav. Okay, any other questions? All right. So thank you for all the speakers of this session. According to the program, we are having a short coffee break. I think that we can allow it because despite the fact that we are slightly behind the schedule, we still have time, and there was a cushion on time for the second session. So unless someone from the speakers of the next session has to run earlier, I wonder if anyone has this problem. I don't think anyone has this problem, but there were some scheduling conflicts. I suggest that we are taking 5 minutes, 10 minutes break. What do you say? 10 minutes?
10 minutes is fine.
10 minutes. Okay, someone bravely made the call. So we reconvene at 5 before the next hour, whatever it is in your time zone. And we will continue with the talks. So 10 minutes break. Thank you. Okay, so it is time for us to reconvene. I hope everyone came back slightly rested. And Anais, you are the first speaker for this session, please.
Okay,
And we cannot
see.
Okay, we can see in the.
You can see it now?
Yep.
Perfect. Thank you very much. Let me hide everything. So hello, everybody. Welcome back. My name is Anais Möller. I actually work in Australia, but luckily I'm in Europe right now because else it will be like 4 a.m. in the morning. And today I'm going to tell you a little bit about one of the brokers of the Rubin community brokers that is called Fink. So this is led by myself, Julian Peloton, and Emily Ishida, but this work is a community-driven work. So here are some pictures of some of the people that have been working within Fink in some of the events we have done both in France, Australia, and even Brazil last year. So whatever I'm telling you today is the effort of these amazing people that are building this community. So who are we? Part one, Fink is not an acronym. It's a name that we liked and we decided to use it. We wanted to be as a broad science collaboration as possible, working with many science cases as we can. And it's community driven and open to everyone. So because brokers, we receive public data. I know everybody here has proprietary data rights, but interesting thing about brokers is that we deal with this public data as well that we can use together with the proprietary data. So in FIC, we have different people working in different topics. Of course, this is not an exhaustive list, and this is something that we want to have even more people working in these topics than others. So we have people working in supernova, kilonova, nuclear transients, gamma ray bursts, solar system objects, space awareness, anomalies, and simulations for LSST. Some of them have parts that are in TVS and then will be important. So today what I'm going to center is a little bit about how to use Think in a nutshell, basically, and how can I talk about TVS science. So let's start with Think in a nutshell. So basically we receive the Rubin a stream in real time, or in this case, we're right now processing CTF as a precursor data. And well, we receive the data, and the first thing that we do is real bogus cuts, which eliminates right now for CTF around 20% of the alerts that we receive. Now we store these alerts, but we won't process them further. So the rest of them we will process with everything that I'm going to tell you right now. The first thing I will do is a cross match, and that can be catalogs like Gaia, Simbad, GCVS, VSX, and Mangrove. Or it can be also survey streams like GCNs, like gravitational waves, high energy physics, or swarm detections. And this is done based on coordinates. Then as well, and we haven't filtered anymore here, we provide features and machine learning scores for different science objectives. So we have models targeting early type 1a supernova, especially before maximum, type 1a supernova, microlensing events, kilonova, multiclass, which you can define multiclass in different ways, and even finding the most anomalous things that we haven't thought about. And of course, this is something that we want to continue expanding. So if you have something that you think that we can use in the broker and you want to contribute that, this is something that we can definitely talk about incorporating. And then you can do customizable filtering, a filtering for your science case, and then you can receive that data in two different ways. I think the beauty of the brokers is that we have something called a live stream. So imagine we have a detection in Rubin, and within a minute or two, you can have it automatically in your computer, or triggering your telescope follow-up, or even like just reporting things. So this is what we call the live stream. And on the other side, we have the Science Portal and the REST API, which is basically accessing our database, which is aggregated at the end of each observing night. And it's a very nice way to start thinking about how can you do science with this type of data. But if you can do it in live stream, then you will have that advantage that you can react super fast. So I'm going to tell you a little bit about how to access the data, whether through the portal, and we have both an interface for our cell phones and the laptop, and the API, which is basically a way to use your terminal or Python code to access our database. So this is a little video of our portal, so thinkportal.org. We have documentation on the left that you can take a look at it. And then we have, for example, you can query the last, in this case, I asked for the last alert that we have received from CTF. I took this video a while ago, so it's the 2020 target. Or you can query by TNS object. We have a resolver. Or you can query also by classes. So classes come in different ways. Some of them are classes based on filters that the community has done, but some of them are from catalogs like TNS or Simbad. But here I'm targeting early type 1a supernova candidate, which is a community built filter using machine learning and other codes. And these are some of the candidates that we have. I like in particular looking at as a table instead, because for me, I can filter with the columns with the number of measurements to get the super mega early or not. In this case, I am looking like less than 10 detections. Then you can go and access the data, and this is type 1a supernova fading now. But you can see things like color, get the DR photometry, which is basically the data release photometry, and we have this for CTF. And then you can explore things like, I want to check SNN is one of the machine learning classifiers. I want to see what data I got from that. You have things like coordinates. You can download the data. It can tell you how to query it from the terminal or your Python notebook, and then you have links to TNS, Data Central, or even like a QR code if you want to share it. We have tabs for different science cases, all of these community-driven, what is interesting for each person in the community. So you can take a look at that, and we are more than happy to hear what you think. Here I'm querying known RLARA from Simbad. Again, I was in the table mode. I changed to the visualization mode. And one of the nice things that we have exploring is one of the tabs of variable stars. We can fold the periodicity with a code. This is actually slow. So you can query that. Let me move this forward and get DR photometry to complete this as well. So each of the tabs have different things, and we are more than open to hear what you think about this. This is the case of the DC magnitude as well that you can do. And now I'm gonna fold. So I was trying to get all the data here. So this works on the fly. Basically, you need to wait that it actually computes this. I took this when I was still in Australia, so it took a little while. So I don't know if I managed to get the result, but you can try it out and have an idea. So this is like the 101 on the portal. Now, we have a service that is very interesting for people that want to download the alerts of a given night or the last week. It's called the data transfer. Please don't download the whole database. You can do it also for Elastic, which was the simulation for LSST. But the idea is that you select a date range, then you select what type of classes you're interested, depending on whether it's Think or TNS or Simbad, etc., or everything that we have. In this case, I'm looking for solar system objects and space debris, and you can put conditions. It's SQL syntax, although our database is not SQL, but you can follow the documentation and it will tell you a little bit about which type of things you can use in these selections. So here, I'm just copy pasting some of the things that are here. For example, here I want something they're quite faint, magnitude higher than 19. And then I say, I want the light curve, I want the cutouts, I want everything. We submit the job, and then you can actually check how things are working. You monitor your job, and then you get your data through our client. So this is great to download large chunks of data. Now we have a limit of how large that chunk can be, because if you want to download the 200 million that we have alerts in our database, yeah, you won't be able to. So this is how you download it, terminal. You just click that and you go through there. The other thing that we have is a lot of tutorials. So you can go to our GitHub and there's a lot of tutorials showing you how to access the data. I'm gonna click in one of these. So let's click on the photometry one, I think. There is a photometry tutorial. For example, you can do all this in Google Colab as well. So you can play with this without resources in your computer. And it shows you a little bit, for example, how to get an object. This is one of the ID objects, how to use our API, what type of data you got, thumbnails, the photometry, etc. And you can do your own science. I think the most exciting thing about Rubin, and we need to start thinking about this, is that we cannot do science a posteriori, in the sense that we cannot do science like, I want to unload the whole Rubin alerts. And the live stream is very useful for doing like immediate science. And right now we have both through the Think client and Telegram access to a lot of candidates from filters of the community, but also catalog and survey matches. And I think a lot of these fit into the TVS themes. We are also trying to have automated system of follow-up. So I'm working in Australia to get this running with the Tom toolkit. So you wouldn't have to wake up and send a target to observation in the middle of the night. You can do it automatically. Just to give you an idea how we're gonna deploy, right now we're deployed in IGC Lab in France, but we will be deploying in the supercomputer in France where we will have Rubin proprietary data. Right now we have processed 200 million since 2019 of CTF alerts. And if you think about scales, we're talking about 35,000 unique IPs and 6 million requests per year in our portal. And the data transfer right now is around 100 million alerts downloaded per month. We have more than 80 users in the live stream right now, and this is increasing very rapidly. So this is the moment for you to familiarize with all of these and exploit the capabilities of the brokers. With this, I end. This is really community driven. We want to hear from you. Our data is public. If there's something that we can chat, more than happy to do that. You can contact myself, Julian or Emily, or contact@thinkbroker.org. I'm more than happy to answer any questions that you have.
Thank you. That all sounds very exciting. Tamas, please, your question.
Yeah, thank you very much. So I would like to have multiple questions, if I may. Yeah, because we were trying out a couple of alert brokers in the past just to have our data collection from, for example, ZTF. And I always hit some walls because the first thing what I would like to ask, is it possible, for example, in ZTF alerts to attach the real object ID to the alerts? Because we know that there is a name for every alert what ZTF is producing. And for example, 20, 25, AA, BB, ZZ, etc. But that is not the real object ID what ZTF is having, because it's I think how long it's 16 character long, contains the filter IDs and etc. And I tried to find it in the other systems, in Lesser, in Fink, and etc. But and we tried to contact you and other brokers, and we always got back the answer that you don't know the original ID of the targets, and it's troublesome, because if I would like to search in the alert system and even also in the real, for example, ZTF, or in the future in the LSST database, I have to cross-match again my targets. I don't know if my question is understandable, but
I guess my question is, what do you call real object ID? Because in the alerts we have the ID of like the CTF 24AATKD.
yes, that is true.
We have
that is
the CAM.
Yeah, that is the alert ID of the target. But
so this is the object ID.
No.
The alert ID is the candidate.
Yeah, that is the candidate. But
yes.
This one, for example, what you're showing, this ZTF 24AATKAHR, it is not in the ZTF database. And the ZTF object ID is not in your database. So I cannot connect the two.
Oh, you mean like for the proprietary data of CTF?
Yeah, because
in
ZTF.
Sorry, I will interrupt both of you. I think what Tamas means is ZTF data release IDs, the same as ZTF reference catalog IDs. I'm not sure if they are in alerts, but if you just use them use Fink through UI, you could jump to Snet Viewer and it will have that one.
Yeah.
Yeah, but I think my problem is in another scale, because if I just would like to see 1, 2, or 10 targets, it's not a problem, but I have over 1 million.
So the challenge here is if it's what Kostya is saying, which I'm guessing it is, this is not information that any of the brokers receive. So we cannot invent what we don't get. Definitely not. But what we can do is there are different things that you can do. One of the things is a subsample has been cross-matched. You can cross-match it by coordinates. And that could be a way to go between the data release and what we have in the alerts. But we don't have access to those CTF IDs. This will be a different case for Rubin, however, because we could have that connection with it. And this could be something we could work towards, Rubin, definitely.
That would be cool. That would be cool. And my other question would be, for example, if I have a bunch of variable stars, and I would like to receive by filters that I would like to have all the data what, for example, ZTF produced for that specific target since the start. And I because I made it in the past, so sorry, just I would like to explain myself better. I go to your site and I write it up, and I would like to receive every RR Lily star under 18 magnitudes and etc. Is Think giving me back all the data from all ZTF data releases, or just the last one?
So we don't use, this is a good question. We don't use data releases in Think. We use the stream only. I don't know where I should show these. We use the stream only, and we have only been here in the stream since 2019. So we have only data since 2019 from the alert stream. The data release is not something that we have stored because we have never received them, and it's not the purpose of brokers. It's the same with Rubin. We won't be ingesting the data releases for Rubin, but what we can do is the type of things that we did here with the light curves. So if there is an API with the data releases, we can query from a specific object the data release to complete that light curve. That we can do definitely. I don't know which part in the video I do this, so whatever yes, I'm here. That we can do.
Yeah, this was my concern, because we try to collect data by alert systems, and this was my problem, that I could only see just a fraction of the collected data. And this is why I'm going back to my first question, that how could I receive the whole light curve data what, for example, ZTF produced? And this is why I had a problem that, okay, I have an alert ID. I know that this is, for example, an RR Lily or a classical sapphire star in ZTF, but I have to find it again in the ZTF bug database. And I know Kostya said, just sent us a link in the chat, but the ZTF reference catalog ID is not the same as the object ID.
It is same. We could discuss it later, but data releases have all the objects from reference catalog. There are no objects in data releases which are not in reference catalogs. So it is the same. If you click for any object to Snap Viewer, you will find exactly that object ID there. Exactly the same you see. Perfectly. But yeah, I think we're going out of the scope of the discussion.
But if it would be made from the start in LSST, that would be a huge help.
Yeah, I think it's a very different survey, LSST from CTF, given that it's not public data, everything, and we don't have data access. But linking with Kostya's comment, we have a SNAT button here, the yellow one there, where you can actually get the link to the SNAT webpage that has that ID. It will be a little bit of convolution, but it's how things are constructed, because if we don't receive the data, we cannot exhibit it. Yeah. Sadly, I cannot fix this right now. But for Rubin, we can think about this, definitely.
Thank you.
Okay, thank you for quite elaborated excursion. Riley, please, your question, and then we will move on.
Hi, thanks, Anais, for the talk. I was wondering if you could say a few words about the Think Science science modules, which, if I understand right, um, allow for like automated generation of like value-added alerts for specific science cases. And I'm wondering, can users create their own custom science modules? Could you say a little bit more about that?
Absolutely. Thanks, Riley, for the question. Yeah, so the idea of the science models, this is how we call um, what we group here as ML features probably, is a way to extract information and even the cross-match. It's a way to add information to the alert. So what we receive from the alerts is basically the detection information, the history, maybe some metadata with like a nearest Kaya value, etc. But we have, like the users are encouraged to propose science models, which means that if you have a machine learning algorithm that you want to apply to create a score, or you want to cross-match with a catalog of a galaxy or something like that, you can add that plus some filtering. And then that will go integrated in our code. And every time we receive an alert, we will go through your filtering and science model. And then you can receive through the live stream or through the Science Portal and REST API your data. How does this work? Right now, we need some interaction. So if you write us at contact@thinkbroker.org and you say, look, I have these, we will guide you through the process of incorporating it. It's basically writing some functions to apply your science model. We want to mainstream these later on, but for the time being, it's like this. One of the things that we really try to evaluate is how fast your module is, and if you need to process it in real time, which is a minute or two, or you can process at the end of the night. And there we can decide differently where we incorporate it in the processing. I'm hoping that I'm answering that question. Was there anything that you wanted to know that I didn't answer?
No, this is all great information. Thank you so much.
Perfect. If you have any questions, don't hesitate to contact us. We have a link in the webpage talking about the science models. Also in GitHub, you can find the code that is Think Science Models, and you can take a look basically how it works. It's pretty simple.
Awesome. Thanks.
Yeah, no worries.
Thank you, Anais. As usual, there is also always a lot of discussions and very pointed questions about IDACs and brokers, which is great. It means that they are in demand. And we are moving to the next talk. So, George, I think this is you.
Hi, everyone. I'll just grab my slides up. Hopefully you can see my first slide. Okay. Mine is a very quick update. I suspect most of you have heard me talk about the UK IDAC before, but I'm happy to answer any questions that may crop up. So a quick reminder, the UK has a reasonably significant in-kind contribution. There's a few elements to that. First of all, we're part of the data release processing. The plan is that we will do 25% of the preparation of the science data from the observatory. We're running an independent data access center, which I'm talking most about today. We are offering a community alert broker called LASA, which I mentioned briefly. I think it's already been mentioned earlier. And we have a number of user-generated products. Some of them particularly may be of interest to this group, but in fact, people after me are going to speak about them, so I only touch on those. There are various other contributions we make, but they're not particularly computational, and I don't look at them further here. So a reminder, the UK IDAC plan, we are planning to run what's called a full IDAC, or at least in the Rubin Tech Note was referred to as a full IDAC. We're planning to run for the duration of the survey, which I think now currently takes us through till around about 2037. That's year 12, so 2 years after the last data release is published before all the data becomes public. Our plan is to host and make accessible the 2 most recently published data releases. So the one that's just out when it is, and the one previous to that. And we're sizing our compute resource to serve 20% of the anticipated community, and that's somewhere between 1,000 and 1,500 scientists. We're running the science platform, so hopefully your experience will be similar to what you have if you log into some combination of data.lssd.cloud. I can never remember which order the URL is in, but the Rubin science platform that I suspect many of you have accounts for. Our DAC is co-located with LASA, which potentially brings some benefits. And we have done some experiments with integration of LASA interfaces with our DAC, which I can talk a little bit more about. We host a number of user-generated products. These are the derived data sets that are taken from the official data releases, usually to support specific science cases or specific science communities. Probably the most interesting is the cross-match crowded field sort of optimized cross-match for selected ancillary surveys, but I think Tim Naylor is going to talk about that in around about an hour's time, so I'm not going to talk further about that here. Probably less interesting, this group, although I'm not an astronomer, so I may be missing the point. We are going to fuse LSST data releases against the Vista survey, so effectively giving you 5 extra bands of color on top of the 6 bands that LSST observes in to support different science cases. And within the UK, we are planning to host a number of ancillary surveys which you may wish to analyze in conjunction with LSST data. The list of those surveys is still to be confirmed, and as we move into the sort of next generation astronomy, some of those surveys will be very large. So co-hosting may be in a sort of network proximity sense rather than at the same data facility. Our IDAC is a little bit different to the project DAC in that we run in an on-prem system. It's a cloud-based system using Scientific OpenStack, which some of you may be familiar with. It is running just now in an early access mode. Some of you may already have accounts hosting early data sets, including some of the data previews. So we have this roadmap here, which we started quite some time ago, and the idea was to share with our early users what functionality, what data, and what services we plan to have mature at various points. And typically, this identifies annual updates to our DAC offering, and currently we're somewhere between UK DAC 4 and UK DAC 5. You can see that UK DAC 5 has slipped by around 3 months. That's primarily because the plan is to host DP1, and DP1 is not now expected to be available to the IDAC community until at least June this year. So if we followed the pattern, we would typically expect DAC version 5 to be available actually next week, but it's not going to be. Looking across the rows here, you can see not as a lot is changing now. It's a reasonably mature DAC. So we have pretty well all of the science platform components running, or at least all of the ones you're likely to expect. We don't actually have image search at the moment, which should be an omission that I've highlighted there and I haven't. We have DP02. We have all of the catalogs from DP02. We have a subset of the images, the deep coad images, and some of the Parquet data. DP02's file set is very large. Given it's hosted by the project already, it didn't seem valuable for us to host the whole of DP02. We also have DP03, and there it is, the full set. That's a much smaller set of data, catalogs only. And coming back to the user-generated products I mentioned on the previous slide, we have some fused Vista HSC data. There we have both images and catalogs. Effectively, what the team does is they run the latter stages of the pipeline, but looking at all 11 bands that you get from Vista and HSC combined. And we have a very small subset of ZTF data release 20. That's probably not useful for science, but it is useful from a software perspective as it allows us to experiment with, I think, what we were sort of touching on earlier, the ability to take an alert and then to cross-reference it against more long-term historic data that's held in the data release. ZTF is also a very large catalog, and as I say, currently we've only ingested a small subset of that. We would, I think, be happy to ingest more if there were particular science cases that needed it within LASA, but I think the actual whole data set is very large and probably would distract us from the work of preparing for DP1. One of the obvious differences between ourselves and the project DAC at the moment is that we are still using GitHub credentials for authentication. This was the mechanism the project was using up until around about 18 months ago. We are still planning to switch to the same mechanism the project uses, which means you would log in using typically your institutional credentials via an OpenID Connect service. However, time is getting tight. We want to get that available by the end of June, but the end of June is not very far away, so that may slip. And in terms of documentation, because we're running project software primarily, there isn't a lot of documentation we need to provide, and we mostly relay the project documentation. However, we do provide specific documentation on the user-generated products that we've added to the available set of catalogs. In terms of support, we are planning to use the community forum. If you want to ask questions about the UK IDAC, if you're having problems or in any way want to discuss with us, there is a topic on the community forum called UK IDAC. It's pretty quiet at the moment, but I think that just reflects the amount of sort of actual science that's going on in these systems right now, and I suspect it will get busier going forwards. So the big changes coming up later this summer, if you're in the Northern Hemisphere. DP1, we are planning to host the full DP1 dataset when it is available in June, July. As noted earlier, it's quite a small dataset, so hopefully not naively, we are expecting that will be relatively easy to ingest. And we are planning to switch to the project authentication model, which means you can log in with your institutional credentials. And if you're a data rights holder, that will be confirmed automatically via the project. DP2, which is the first LSST CAM data, if my understanding is correct, it is currently expected around May, June next year. Again, we are offering to host that data set. I don't yet know if it's confirmed that DACs will get that, but I think it would seem sensible, and I don't see an obvious reason why they wouldn't. And then DR1, currently we've got that set for March 27, but actually that might be a little bit late, depending on how well early operations goes. It's possible that DR1 will be published at the end of 26, so that date may go forwards. By DR1, we should be in full operations, and as I say, we'll be expecting to service around 1,000 users. A brief mention of LASA, although I'm not involved in the LASA project, and already some of the questions that were asked about Think, I think I have no idea how to answer those questions. So hopefully some of you are aware of it already, and I can certainly put in touch with LASA if you're interested. It's one of the main community brokers. It provides a filtering service for the real-time queries based on an SQL-like interface. So if you're familiar with SQL, as I'm sure many of you are, it should be relatively straightforward to create filters or queries that can be applied to the live alert stream. And the idea being that you create things like watch lists, which are your favorite objects or favorite areas of the sky, and then you will receive alerts if something interesting happens in those watch lists based on the sort of criteria you've set. There is a built-in classifier, it's called Sherlock, which aims to give you a first indication of the likely classification of each alert that's raised. It's running already, as with, I think, probably most of the other brokers. It's using the ZTF alert stream. If you wish to go and try it out, you can. The stream is public and access to LASA is public. The URL is there. At the last check before Christmas, we've got around about 500 users registered. So it's probably the most popular bit of the UK DAC at the moment. And I think there's around 81 publications have acknowledged LASA as their source for data analysis. We do support some downstream activities, things like telescope follow-up and the like. So having consumed a Kafka stream, we can then emit a further Kafka stream onto other services. There is a system called ePesto, which is using this function just now to allow sort of follow-up of certain targets with spectroscopic observations, which I think is using the Foremost telescope, but that may be incorrect. So as I said, that was a very quick talk. In fact, I didn't even put a thank you slide. Apologies for that. But if you have any questions or if you'd like any more information, I'm happy to try and help.
Thank you. I think it was quick talk, but packed with useful information. So it was great that you had time to show up and give this intro or update rather. So questions, everyone.
Cool. You're back on track.
No, I think what? Okay. Yes, Tamas. I was expecting that someone will have a question.
Yes, I have. I have many, but maybe we are a bit behind schedule.
Behind the schedule, yes. So
yeah, I was just looking at the numbers, account numbers, and if I remember correctly, in Europe there will be this IDEC, maybe in France, and there will be a light IDEC. So I think for European scientists, the UK IDEC is one of the most important. But just looking at the accounts, how will this work? So if I know there are 300 PIs just in the UK, so there will be enough slots for international users, because just at the last column there are 1,000 accounts, but if I just run a quick head calculation, it is not enough even for the British scientists.
So our expectation is that with 1,000 accounts in the first year of operation, it's probably going to be about half and half between UK and international scientists. You're right. If you think of it as sort of the obvious choice for European scientists, there isn't enough there. But we do offer the same services as the US project, and there's no reason why you would necessarily choose this over that unless you're interested in some of the derived data sets, or particular science communities may choose to congregate around the UK DAC. It's what we offered. It's based on what we can afford to offer. If you look at, I think it's RTN 008, it defines an average compute requirement per user.
Yeah.
And it's the compute we're offering is sized based on that. So how we control access, I think, is still unknown within the IDAC community, to be honest. It could be. I don't think we will get to the point where we hit 1,000 and then we will not let anybody else log in. But it's sized based on the expected compute load from roughly 1,000 users. They may not always be the same 1,000 users. And because of the API approach, in fact, other IDACs, there was talk earlier about how you would get how you would get deep COAD data, for example. It could be that you actually query our interface from another IDAC to receive the COAD information you need, which is a computationally less intensive operation than logging into our science platform, spinning up an Ablado notebook and running various scripts. So it's a guideline we've given to the project to say how much compute we're going to purchase, rather than a very strict limit on how many user accounts we will allow at any one time. But obviously, if 10,000 users log in, it's going to be very slow, it's going to be very unpleasant, and we'll probably get lots of rude emails.
And if I may have a second question, will be there any notes for the community that, okay, we have now OpenID Connect and that's register at our site, so how will it go? So if I would like to use the UK IDEC in the future, how can I be sure that I will have access to it?
So it should work in the same way as is the case with the Rubin Center, in that the first time you visit data.lsst.cloud, or whichever combination of those three words it is, you register for an account, you use your institutional credentials. Usually within around 24 hours, you get a confirmation. Hopefully that will be automated. I think at the moment there is a certain manual check against the list of data rights holders, but the plan is that that will be automated. And you do the same, and once you've registered, you can log in as and when you wish.
Okay, thank you very much.
Okay, thank you. Tomislav, if you have a quick question.
Yeah, I had maybe a little bit more like a comment that if you take into account that there will be no open public French full IDAC, so I think the UK will be the only one. So I expect that all the Europeans, first day of data release 1 will run to your IDAC. so
day 2 they'll go to the project, I'm sure.
And because I mean, if you know what happened with the Gaia data release, so it was the same thing. It was just you could not connect with their server, so it was total rush on data releases of Gaia. So I had just one question: will you register the users up to some number that you make like a limit number, or you will register everybody that wish to go for your IDAC?
I think the question is, we're not sure at the moment. So we are going to use demand management, but it is unlikely to be as sort of blunt as number of users. It's likely to be related to the amount of data you can retrieve at any particular point, or the amount of compute you can secure at any particular point based on other demand. We're talking to the project about this because the project has to do the same on their science platform too. So it's likely to be topical. When you log in on day 1 of a data release, your access to resources is probably going to be limited. Your ability to query is going to be sluggish and slow, but maybe you come back 2 months later and you'll find that it's easier to spin up larger VMs, notebook services, sorry. You'll find that queries are more responsive. It's a bit of an unknown at the moment, but yes, we are aware that Gaia fell over on day 1, but there is demand management constraints within the system, which means that if there's too much demand, then the user experience deteriorates rather than the service crashes. Let's hope it works.
Yeah, let's hope. But I mean, this is much better than to limit the number because of the fairness and openness and all those things.
Sure, and I think I don't even know how you'd manage it, because 400 users log in on day 1, 300 never come back. Have we sort of siloed 300 accounts that will never be used again? So I'm hoping we can do something quite a bit more dynamically than that, and in reality we'll have more than 1,000 users registered, but maybe only about 1,000 active at any particular period of time.
Okay.
That doesn't mean 1,000 logged in at once, by the way. I mean 1,000 active as in visiting us every week or so on.
Thank you. And at this, we will have to pause this discussion. Maybe we will continue it with
Sure. Happy to chat on Slack or on email. Slack's probably ideal. Go to the IDAC coordination group.
Definitely. And next talk is Andrea, also about light IDAC. Please go on.
Okay. Hi, I hope you see my slide. So my name is Andrea Gomboc. I come from the University of Nova Gorica in Slovenia, and I will really briefly just present the Slovenian light IDAC ideas. So this is one of our in-kind contributions. I hope you see the next slide. So it is, we promised to give a light IDAC for the LSST at Vega supercomputer in Slovenia. So we pledged 0.5 petabytes of storage for 13 years and 20 mega CPU hours. Currently, we have this Vega HPC with these performances, as you see here. End of life of Vega is in 2026, but the new HPC Vega 2 is on the way. So we just got, Slovenia just got approved funding from the EU and from our government. So it will take over, it is planned that it will take over and that it will be even better. So we are still collecting ideas about what to use this light IDAC for. So if you have a good suggestion, you're most welcome. So for now, we have the idea that we would offer on this light IDAC TOM, or some kind of portal for nuclear transients. So we would store just data on this type of transients, and we would then enable users to upload their data to plan observations and do some analysis on this data. Also leave comments. So for example, we took a spectra and we find that this is a supernova or AGN or whatever. So this is our idea. We were exploring two options so far. One is the Fritz Sky Portal, some kind of smaller version, just for nuclear transients, or Tom Toolkit. But if you have also some other ideas, we are. It is not too late, so we are open for suggestions.
Okay, thanks, Andrea. I right away have a question. Maybe I missed it. So what about the network capabilities? How many users will be able to connect? What about the possibility to transfer the data? Do you know anything about that?
Okay, so I'm not an expert on HPC. We have one researcher who is a top expert on that, and I'm sure he could answer all this. From what I know from him, so far when we asked these things to him, he said no problem for anything. So it is connected, it is professional. So, but sorry, my apologies that I cannot answer, but I can connect you with him so he can reply to that.
Well, no worries, but I think that it's a good idea if someone who's going to build this will be at the next big meeting able to talk about this in more detail, because no problem with everything means that we are coming and asking for a full IDAC with transferring data back and forth.
No, this light IDAC is just a tiny fraction of this Vega HPC, so I'm not worried.
Yeah, so probably not anything. Okay, any other questions? Okay, I suppose that we will have a lot of questions next time when there is a more detailed presentation. And we can move to the next speaker. I think it's Anjoka, is it you? Let me check.
Hello, everyone.
Yes, hello. Please go on.
Thank you. Okay, I will just slideshow. And hello once again on behalf of the CERSAGAS One team. Beside me, here is also our program manager, Dragana Ilic. And if you have questions for us, we are more than happy to interact during the discussion session. And I am in-kind contribution lead of Directable In-Kind software contribution. That is actually a Python framework for neural process modeling of the red noise light quasar light curves and the periodic analysis. We already organized a demo session in April 9th, 2024, that is actually announced across the LSST Slack channels in TVS, AGN, of course, and on Announce General, and recordings are available at our data cloud that was actually kindly granted by TVS Kickstarter program in cooperation with the Hastings-Simmons Foundation. As we go to our framework, we can actually position our two packages, one that is called QGX Quasar Harmonic Explorer, and the other QNPy that is Quasar Neural Process in modeling in the Python. And what we want actually from the scientific side to actually disentangle the structured information that is actually embedded in the red noise. For example, it can be periodic oscillation, but also using quasar neural process model, we want to infer the most relevant information that is embedded in the red noise light curves. So both of our codes are actually in this hub that is actually want to extract temporal and periodical scalings. So both of our codes are operating on the, can operate on the single, but also can operate on the larger number of the quasars in order that we can infer the population level features that can serve for information about the scalings across the large phase spaces. And one of the scaling relations, a recently published investigation that, like the precursor for the LSST, is given by, for example, by Petreka in 2024. And when we are coming to the periodicity detection, what we can see in AGNs, in difference, for example, to the stars, we can talk about the information that is not, how to say, perfect sinusoid. Maybe in difference to the stars, you can have the perfect oscillator. One example of the perfect oscillator, if we transform light curves, for example, from this AGN candidate, it looks in the phase space, Hilbert phase space, almost like perfect oscillator. But we have some other famous binary candidate, and we can see here a transformation of its light curves are not perfect oscillators. So when we are talking about the detection of the oscillations in the various objects, we can be aware, are we talking about expected perfect oscillators or something that it is not perfect. From the community positioning of our codes, as it was emphasized in 2023 at the Project Community Workshop by Agnieszka Polo, that we actually need new methods for the clustering and in different parameter spaces. So both of our algorithms are extending the parameter space for detection of the oscillations behind what we know for standard Fourier-based methodologies into new period phase space. And for the quasar neural processes, we are extending and adding new type of the latent space that is actually context aware, in difference to maybe variational autoencoders which are actually learning the whole light curve at once. So we are context aware. What is the important context in the light curve we are investigating? As for the software status, we actually published the softwares in the latest version for the Quasar Harmonic Explorer is 2.02, and it is released with continuous integration and deployment pipelines fully passing, and it is submitted to the Journal of Open Science Software, Journal of the Open Science Software. And as for the quasar neural process, it consists of two flavors. We published the conditional neural process, and which was released in March 2025. And then recently, we actually upgraded this into the more attentive and latent version of the neural process. As for the pipeline, what we are doing, we are actually extending detection of the oscillations in the light curves based on the wavelet transformation of the light curves, and then we are cross-correlating them. So we have the input light curves, they can be modeled, they can be raw, whatever, and then we are actually inferring the correlation density of the present oscillations into them. What is the difference between our methodology and what we know from the Fourier methodologies? We can, in Fourier methodologies, infer single time slice of the present oscillations, that is the top of the ocean. But if we want to look into the depth of the ocean, we need to use the ultrasound methodologies, and that is akin to the wavelet transforms. In wavelet transforms, we have the scales, for example, in similar to the depth of the ocean, and then we have the frequency. But from this, we can infer the planar view of the bottom of the ocean. The ocean, in our sense, is the AGN, what is happening there. However, if I have the other source of the ultrasound, in our case, the other light curve from the other band, then we can also infer the other planar view of the bottom of the ocean of our object. And with the cross correlation, we are actually inferring the inference patterns from both of these wavelet transforms, giving us possibility to present the the correlation, cross correlation density of the present oscillations. On the main diagonal, we have what is the mostly actually present of the oscillations in the two light curves of diagonals, are speaking of some specific maybe events in the object that like, for example, mergers. And we are capable with our methodology to produce the detailed secondary catalogs of the detected oscillations with the significance, with the saying in which bands. We also devised new type of the metric in order, because we can actually detect periods in the multi-bands. The basic band with which we that we are using for the reference and comparing to other bands is the U band, and we are actually inferring the overlapping of detected periods across the bands, pairs of the bands, through the intersection of union metric. And then we are offering the classification, and then we can also provide the new type of the presentation of detected periods in the plane of the object ID and period detected, with circles corresponding to the radius of the relative error of detected period. As for the quasi-neural process, that actually we actually released a conditional neural process, which is actually nothing else than inferring the general representation through actually through aggregating mechanism. And then we are learning the distribution of the most, of the all probable models that can pass through the data, and then we are inferring the mean and the confidence level. That is the Bayesian, inference. But in the attentive latent neural process, we added new arm, that is the attention. So it means that we are paying more attention to more relevant data in the context points, and also we are adding the latent module in order to infer the most probable to infer latent information, such as, for example, the model of the transfer function and supermassive black hole parameters. Of course, we can combine both of these packages into one according to the theory by Baker and from 23, and that will be the next level. And we submitted the paper by our colleague Raju, who actually worked on this upgrade. As for the architecture, for the QAJAX, it is the modular design. We are using the WZ method for the wavelet transform, and superlets are something that we will be more tested in the future. And what is interesting, we also have the in this modular prescription, the handler for the data that is called data manager. So initial version of the QHX was actually according to the LSST data, but in the latest version, we added the dynamical module, which can actually map the data from any other catalog, like, for example, Gaia or whatever, in order to be actually executed in the pipeline. As for the QNPy, as I said already, that is the neural process. And importantly, we also implemented the self-organizing map in order to cluster the light curves before application of the neural process for the modeling. The reason for this is actually that we stratify and light curves according to the information they have inside of them that is not so easily seen by humans, and also to speed up calculation if we actually partitioning the large data set into clusters. And one of the advantages of the neural process that it is actually doesn't need a large amount of the data for the training. For the autoencoders, variational autoencoders, we need the millions of the data in order to be trained by, but neural process should be light in that sense. As for the intersection of the union metric, that is the new type of the metric for measuring the overlapping of detected periods in our pipeline. And actually, if we have detected periods, this is these dots, we can construct the relative error for them, and then we can circle the balls, and then on the base of the intersection of these balls between the various pairs of detected periods, we can actually use this as an additional statistical metric for detected periods. And as for the scalability, we actually we applied this at various at two types of HPC. Firstly, we are really grateful to Bura for application of our codes, as mentioned by Tomislav Jurkic in his talk. And then we are also applying to the governmental AI platform, and also to our department HPC modest unit. Here we can have just the example of the computational expansivity of our tasks that are calculated for the Weyl transform matrices that are most expensive. Why? Because we are going into another dimension in difference to the Fourier methodology, which is only doing calculation in one dimension. But as we are expanding in the second dimension, it means more power we need. And for example, here are given actually the some of these calculations that, for example, we need between 32 days up to 100 days for example, for the 800 million matrices. And some examples of the results of our module, of our application of the packages for the Quasar neural process. As we said, we are doing the clusterization of the light curves, and with this we are actually doing something that is kind of the positive and negative focusing of the information. The negative is in sense that we are partitioning the input catalogs into the highly abstract spaces. And then the positive is this, that we have the concentrated information of each light curve in that space, as it is represented in these means. And here is, for example, from the ZTF data, how it looks like the clustering pre-processing for the Q and pi. And here we can see the results that are submitted to the A&A journal. And we have been using as the ansatz of the cadences, these types of the cadences, and the results are actually really promising. The latent space can encode information on the transfer function and also on the supermassive black hole parameters, and also for the recovering of the light curves. And for the QAJAX, we can see actually that here is an example for the fiducial object binary black hole for the LSST detection. The most promising candidates in the space that is parametric space of the semi-major axis and the eccentricity, as they can both be actually imprinted in the optical light curves, is between these 0 and 1 sigma contours. And as we go into larger, more massive objects, we can see how it is actually become really complicated to detect, because we are bounded by the upper limit criterion of the 5 years for reliable period to be detected. And we can see here the performance of the QAJAX. The left plots display extracted periods for the AGN data challenge and ZTF data release 19 light curves across multi-band. And on the right, we have actually artificially injected periods of 50 days with varying sinusoid amplitudes of 2, 3, and 4% in the AGN data challenge light curves. And we can see as the amplitude increases, the injected period becomes more prominent, and with other periods are increasingly suppressed. So this highlights that the QAJAX can actually detect the periods. And of course, we can use it for the detection of the emergent behavior. And here are some possible application. And here is the illustration of the merger signal artificially injected in the LSST AGN data challenge. Here is the publication with the Italian and Croatian representative Marta Fatovic, and also submitted papers. So here are the repositories, and we would like to thank you. And we have some also notebooks, so it can be reserved for the discussion. So thank you so much.
Thank you, Angelika. Quite information-packed talk. You managed to put a lot of new results here. I cannot fully follow it, but I recognize that there is a lot of new things. So we have time for maybe one quick question. Monica.
Yes, thank you so much. Thank you, Angelika. It's a fantastic job you do. I just wanted to ask about the cadence of the observations that you need from the LSST, and how many data is the minimum data that you need for detection that you have described?
Angelika, we cannot hear you.
Okay, apologies. Thank you, Monica, for this important question. As for the QAJAX, Quasar Harmonic Explorer, and also for the Q and pi, we need 100 points to be in the light curve. You know, whatever is the observational baseline. So As for the QMPI, it can actually follow up the modeling, and something similar when we are experimenting with ZTF and with other, we found that we want to have at least 100 points, whatever is actually the baseline they are covering. So that's it. Even it can, for example, for QAJAX, we have a possibility in the examples notebook that you can try to, you know, to make your own experiments, but there to inject data points, for example, about 80, 90 over the observational baseline. So, but that is what we expect. At least 100 of them.
Okay, thank you. Which is not a little number of observations for OSST, but still, it is pretty complicated light curve that you are working with. Okay, thanks, Anjoka. And we have to move to the next talk. Stephen, I think it's yours.
Hello, everybody. Let me just a second to get my screen shared. And the perennial question, can you see me? Can you hear me and can you see my screen?
We can hear you and we can see you as well.
Alrighty, I'm just going to slideshow mode. Okay, so I'm talking to you on behalf of the Canadian Astronomy Data Center. I'm actually talking to you from Europe right now because I'm currently in Leiden at a Euclid meeting, ironically. Come on. Oh, too far. Okay, so the Canadian Astronomy Data Center has been around for since the 80s. We are a multi-instrument, multi-telescope archive for all of Canada's telescopes. So that includes JWST and HST, which have a slice of which are Canadian, Canada Fancy White Telescope, and Gemini, but also about it's a dozen or so telescopes and 200 or so instruments. Our current holdings are 2.3 petabytes of data, roughly 300 million files. And our main thing for years was delivering that data to not just Canadians, but to the world. So annually, we would have a data transfers of about 100 million files, about 5 petabytes. And our users were predominantly international, so only 15% of our customers are actually Canadian. A couple of years ago, we moved from just being a data archive, a data repository, to also hosting a science platform. So we have a user data storage, so not just the archive, but you can store your files, your advanced data products on our system. That's about a petabyte or so of data at the moment, but our allocations start at 200 gigabytes and move up to rapidly to 1 or 10 or possibly 100 terabytes for the largest customers, largest users. With fine-grained access control, so you can share the files or not share the files. You can keep them yourself, share them with your group, or share them, make them public. We also offer processing. So the first version was back in 2008. It was based on OpenStack VMs. It was very powerful. It was really quite useful. I still use it, but it was not particularly user-friendly. And then starting in 21, we moved to a container-based, Kubernetes-based system that has Jupyter notebooks, and then another interface, which is not illustrated here, which is a VNC desktop. So it just looks like an old-time Linux desktop, but it's actually running on our system in your browser, but running on our system. And every time you open a new Xterm, you're actually opening a terminal onto a new computer. So you can get a fair amount of compute hardware without even having to go to batch. The key to this was the ability to share containers, and that means you can share software. So much like Google Play or the App Store, Google doesn't write that software. It's somebody else, a third party. and the ability to share containers among users using the same access control as the data allowed a lot of groups to do an awful lot of science. And so you can bring your own software to us and install it and have that run on our system. It's portable. There are multiple instances running across in multiple countries, and it's been quite successful. So about a third of Canadian astronomers are users. Right now, it's just looking at the system. There's 150 users on the system right now. Overall, there's about 500 people who have accounts, and those numbers actually are out of date. We're rapidly increasing the number of cores available. And this is because of SKA, so that's not really strictly relevant to this LSST-focused discussion, but we're an SKA partner, and we are going to be growing substantially over the next few years. So by the end of the decade, instead of having 2 or 3 petabytes, we will have 80 petabytes of spinning of disk, and then nearline storage that will grow by 50 petabytes a year, and they'll grow from 2,000-ish, where 4,000 is now, to 40,000. And so the CDC's LSST efforts fit within this SRC envelope. So for the LSST, we're building an IDAC Lite, and so for each data release, we will host co-edited images, which total about 2.7 petabytes. You can retrieve them using the existing set of CDC tools, so data discovery, data download, and all the rest of it, much as you can all the other CDC's holdings. We'll have an object light catalog, so that's the static sky with a restricted set of columns. That will be actually probably our biggest challenge. We know we can expand our CPU and storage capacities, but databases on this scale are a bit of a new thing for us. For each of the data releases, we'll be providing 3,000 cores for user processing and providing 2 petabytes of user storage. And so there's actually 2 batches of those resources. So the first is for Rubin data rights Rubin data rights holders starting with DR1, and then when DR1 becomes public, we will double our capacity for LSST and make the same set of resources, or a copy of the same resources, available to the wider astronomical community as part of our contribution to Rubin. The access we provided by the Campfire Science platform, which is a little bit like the Rubin Science platform. We offer substantially more cores and RAM on a single node for users. So when users come in, they can select a flavor, and if they need 1 or 2 cores, that's fine. But if they need 32 cores, then they can get that and more RAM for larger jobs. And so the same notebooks and virtual desktops and user-contributed software. Possibly by the end of this week, we'll have a functioning we have a functioning batch processing system, but we will have a smoothly functioning batch processing system, which will not make it very easy for people to overwhelm the system with better queue control. Is basically what will happen to will be added to our current batch processing system, which has been used for the last 4 or 5 years, but has required an awful lot of user discipline. Yeah. So how we think we'd be best used by Rubin. So based on our experience with Campfire, our usage is there's a large number of users that require very few resources. So 1 or 2 cores is fine, and not too much storage and not too much memory. And then a few users require sort of the 100 terabytes or more, multiple hundreds of terabytes of storage, hundreds or possibly thousands of cores for a period of time. But then there's another class of users, which is quite large, which is sort of halfway in between those 2 extremes. And so we think that Rubin data rights holders we're best tuned to users that require a bit more power than the Rubin Science platform provides, but not the kind of people like, say, Dask, who are going to require thousands and thousands of cores for months on end. We're not well tuned to suit them. We are open to a different process if that's what is what decided, but it's not at least currently our first choice. For DP1, we're still seeking clarity. We're not sure what's going to be available to us and when we're going to be able to host it. And the authentication authorization, at least for DP1, will almost certainly have to be the existing CDC access control, where you need to require a CDC account, and that we would have to manually link with any Ruben credentials you might have. Yeah. But our current expectation will be hoping to add the static co-added data set, although we could, for DP1 at least, have the full source time series, but that would be, we don't want to get people used to that idea, because that's not going to be possible starting with DR1 with our current budget. Although, see the next slide. And then the data would be available to existing data services, or tap database access, storage inventory, file access, and our current access control. So what can we do for TVS? So at first look, it's not obvious that we're a good fit for you, because we're an 8.5 organization, not 24/7. And we don't currently plan to host any of the time series. However, we do provide a flexible and powerful platform. So if you have ideas that you want to do that are not sort of down to the nearest seconds after the alert goes off, there are an awful lot of things you can do with our system, and a lot of things that people have done with our system. And it's very easy to bring your own code to our system. And then the last week we had a visit from Nevin Kaplar from the Link group in Seattle, who talked to us about HATS, the Hierarchical Adaptive Tiling Scheme, which I see there's a talk a couple of minutes from now going into that in more detail, so I won't go into any more details myself. But that looks like a economical alternative to traditional databases. And the example he gave himself, because that's what he's interested in, is light curves and ways to do period finding on light curves in a fairly lightweight way to do it. So that might be something that will be happening. So watch this space. Thank you very much, and I'm open to questions.
Thank you. Okay, are there questions from the listeners? Well, actually, I have questions. I mean, they're not probably for you, but still. So that brilliant slide that says it's still not clear when and how the data preview one will be accessible. So considering the data preview one is going to be released like in a few months, do you have an estimate when will you know how and when it will be transferred to your IDAC?
Yeah, so the how is pretty obvious. It'll be Ruscio. So we're actually, I see Knut is on the call, and we'll be talking to him on Friday with updates. The short answer is it looks totally feasible. The people the hardware we have is run on an organization called the Digital Research Alliance of Canada. They've been working with particle physicists for decades now, and they have extensive Ruscio experience. And so the data transfer we imagine will be short and sweet, and will take less than a day. It's just a question of which day that is, whether we have access to the data before the first look event, or whether which would be great, because the part that will be time consuming is not the transfer, but the ingestion into our systems, where we'll be doing something new, and that could take a week or 3.
Okay. So, okay, if there is no other questions, another short question. When we are talking about batch access that is going to be re-implemented, it will work smoothly. About what sizes of batches we are talking about? So essentially, if I want to come and get access to, let's say, a few dozens of thousands of cutouts, like Is it feasible or is it too much?
Dozens,
Of
it should be
thousands.
feasible. Thousands simultaneously or thousands spread over, like you download a thing, you process it. It's a question of simultaneous access. So
Okay.
currently, we've actually lost the ability to test how, I used to have jobs where I would run thousands of cutouts. And
Okay.
if it was 1,000, all was good. And if it was 2,000, things started to fall over. It was 3,000, that would be game over. Since then, we've updated our storage system. But since then, we've also restricted the number of cores that Stephen Gwynn has simultaneous access to. So I have yet to cause it to crash, but I've only tested at the 500 core level, not the many thousands. I am told there's no, that will be fine. And for something like SKA, where the files are huge and cutouts are important, that has to be something that we are able to provide usefully. And then, but it's also a question, so simultaneous is the key thing here. If it's one cutout and then you download the next cutout instantaneously, then that's different than if you download a little one cutout and then do a few seconds of analysis on it and then do it. So the number of
Yeah, so
simultaneous.
stream is okay.
Yeah, exactly. Makes things easier for us.
Okay, thank you. I think it will be useful for quite a number of people around here, even despite the absence of light curves, as you say. And
Well,
if there
possibly. What, as I say, watch this space.
Okay, we will keep an eye on you. Okay, thank you. And we move to our next speaker, who is Alex Razem, apparently. And Alex Razem has to share her slides and screen. It will take a few seconds. Not one thing. This is the right thing. So hello everyone. I will try being really short. It won't be hard. So I'm Alex Razem, and I'm not from Ruđer Bošković Institute anymore. I'm from University of Nova Gorica of Slovenia, starting like 2 days ago. But I'm talking about an in-kind Croatian in-kind contribution that goes to the Ruđer Bošković Institute in Croatia. And this in-kind contribution is the development of TVS Dash, which was originally envisioned as a portal for accessing and investigating light curve data. But since it was the original project that was proposed like over 4 years ago, and since a lot of things weren't possible to implement back then, the project changed its shape several times, and currently it is down to a pretty humble Python library of visualization tools for light curves. Let me check if I can hide some things that are interfering. Yeah, okay. So the original, it was directable in-kind contribution, and the original purpose was to develop tools for investigating variable sources in OSST data releases, and possibly to develop a portal that would serve as a gateway for all the various tools, projects, software projects developed within TVS science community, so that it was like a place where we would gather all the instruments that we develop and where we would provide a convenient access to this. Now, original functionality was rather serious and rather expensive. But once again, it was 4 years ago, and we actually developed a very proper software documentation, software requirement documentation, software design documentation. And when we looked at all of this, we figured out that a lot of functions that we promised to provide, such as ADQL selection interfaces, such as some of the plottings, we figured out that a lot of this functionality is duplicates already existing functionality, provided at much better scale and quality in many data portals in NeuroLab, in Ruben Science Platform, and so on and so forth. So we eventually figured out that, okay, all those complicated things that would require us to develop databases for users and data access functionality, we will cut it out and we will concentrate on visualization things, which diminished the scale of the work significantly. So currently what we are doing, well, what I'm doing, or what I was doing, since currently it's not very clear in what status I am since I changed the institution, is developing this Dash Python package that would be a collection of visualization components that would be convenient to use out of the box for the light curve investigation. And we are using for this the interactive packages from the HoloViz system, with which I think those of you who worked on the Ruben Science Platform and went through the data preview tutorial notebooks, you're probably familiar with this stuff. So HoloViz libraries are a set of packages that take interactivity very seriously. So this is not visualization libraries for, let's say, creating a plot for your paper, but this is something that you would use interactively, either in your Jupyter notebook or maybe on a separate website to quickly change different parameters and see what kind of plots you can obtain from these different parameters, and maybe figure out something useful for you. So if my computer doesn't crash, I can probably show you a small demonstration of what we are talking about. Is it going to? No, it's not going to crash. Yes. So what we are talking about is stuff like this. Let's say we want to inspect certain light curve from LSST dataset. So above, I opened already several datasets, including LSST, that contains a number of observed data points from several light curves of several objects that are all RR-LiLAC candidates. And after doing minimal pre-processing, I'm creating this component, hard to say what would be the best name, but essentially a small dashboard for my own science. What I'm putting here is essentially a set of controllers. So one controller is to select an object, another is to, for example, set the limiting magnitude, to select the band, so to switch between fluxes and magnitudes, and to build a periodogram to display it either with frequency, power, or period power axis. So this one is exclusively for Lomscargo, just for simplicity, but generally you can connect as many algorithms as you want. So essentially the idea is you are having an interactive dashboard for your specific science case in your notebook with just a few lines of code, since HoloViz system is pretty convenient. And the idea that we are building a set of these dashboards packaged into a separate package. And this is something that anyone in the TVS community can use for their own investigation. So that would be convenient, for example, for inspecting many light curves in different bands, for seeing how different period finding algorithms, what kind of periodograms they produce, or what kind of folded light curves. Adding, for example, cutout viewer also to see simultaneously light curves and cutouts, and stuff like this. So essentially, it is more or less like a data interface that you can find in a Brocket page, only specified for your science. And additionally, these kind of things can be served both in Jupyter notebooks, also within Ruben Science Platform interface, or it can be put in a separate website. Also, this is done pretty easily. And it can be built in either into a HTML website or into Django website with preserving the same functionality. Yes, PSF Flux not a good idea because the scales are different. This is something to set up. Plus, additional functionality is more detailed inspection of separate data points. So, for example, we can look at what kind of output the period determination algorithm gets. We can mark certain periods as with some labels. So, for example, we can say that this is an alias or the byproduct of something that results as a result of an overlap of an actual light curve and observational cadence. And then this data can be processed further. So this is essentially a good tool for any kind of manual exploration. So this is what is being done now, and switching these things doesn't work well for me today. So this is the current state, is that in addition to a lot of documentation that was prepared in the old times when it was still envisioned that it will be a portal, there are some Jupyter demonstrations and some of the components that are being prepared in this package. But what is currently, so what is the current state of the work is that while developing this kind of stuff isn't particularly complicated, and there is very little of actual code in there, although the libraries are a little bit glitchy. The complication for me, essentially since the beginning of this work, was that it's pretty hard to develop a universal kind of visualization.
I know.
Yep, this is still me. So essentially, this kind of component, this kind of dashboards, I've been developing for my own science cases, which were not numerous since I didn't work with light curve inspections many times in the last several years. So essentially, this is like a collection of bits and pieces that were useful to me across time span of several years. But with not a clear understanding what would be useful for the TVS community. So the output here, considering that we are nearing the actual data releases, is if you think that you need something for inspecting this data at scale and for which you would need a good and convenient interface, then this project is very much has the whole TVS community as the recipients. So please get in touch and let's see whether we can develop something that will be convenient specifically for you. And other than that, it will continue as it is, probably indefinitely, since I am making this for my own use mostly. And that would be it for now. And thank you. I think I am well within 10 minutes. Questions? Yes, Costa.
Thank you so much for the demo. Sorry, maybe I missed it, but what are the programmatic interface for loading the data in the framework? Does it always go through RSP, or could I just bring my own favorite light curve from Rubin and plot it?
Yes, so you can easily use your own light curve. So since the original project was envisioned to be more or less universal in terms of where you can have the data from, there is additional small package, not small package, but collection of functions for converting the data that comes from different sources into format that is okay for the visualization modules. So mostly, obviously, it was developed for LSST format, but you can, in principle, use it with any light curves. I was experimenting with Kepler. I think I was looking at the ZTF. So in principle, no, you can use whatever light curves you want. But if it is something that is not in the LSST format, then you have to write the data format converter, obviously, because everything is different, right? But in principle, sure, you can use whatever.
Thank you so much.
Any other questions? None? Then we can use to the next speaker. We can switch to the next speaker. And I'm confusing language now. Costa, you are the next.
Yeah, hi everyone. I'm losing my voice, so if you stop understand me, please let me know. I'll try to do something. So yeah, hi everyone. I'm Kosta Melanchev from Carnegie Mellon, speaking on behalf of Link Frameworks, the team dedicated to develop scientific software and enable LSST science through software. We are between three universities: Carnegie Mellon, University of Washington, and University of Pittsburgh. And I'm project scientist in this team. So today we'll talk about HATS and LSDB. HATS was already mentioned a few times. Thank you everyone for mentioning it. So I'll try to give you some idea what people were talking about. So the idea of the HATS is to develop a format, a spatial partition format for scalable catalog analysis and catalog cross-match. So let's say that you have Gaia Gaia data, and you would like to analyze the whole catalog or significant part of the catalog, right? So it is pretty large, right? So you probably would like to run parallel analysis. You also would like to run it out of memory, so not all the data at once in your RAM, because you don't have RAM large enough to load it. So let's split the data, and the way we do it is using Hillpix tiling system. So, and here each diamond is this Hillpix tile, and of course in more dense regions we have smaller tiles. So all the tiles having, you know, roughly the same number of rows. So here I believe it is something between 500,000 and million rows. So what you could do with this format, you could analyze the single catalog, again, just loading the data by these partitions one by one or in few in parallel, or you could cross-match multiple catalogs together, again, without loading the whole thing into the memory, without building any supplementary indices, because you already know that if your object is here, to cross-match it, you just need to load to this partition and this large partition, right? Then you're getting a cross-match result. So we developed this HATS format and LSDB package. LSDB is a large-scale database, which we use to, which is a Python implementation of this framework working with HATS data. So of course we have a cross-matching algorithm out of the box with LSDB, and we also have some analysis tools. So when I'm saying that it is scalable algorithm, what I mean that it actually could do stuff faster than usual tools when we're talking about millions or billions of objects. So you see here we cross-matched ZTF without light curves, so just metadata and Gaia, few columns only, and it could be done in under a minute. Well, very well under a minute. And if you need larger scale data, of course, it will just take a lot of time to load it from disk and save it back. But so it will be your, you know, limiting factor, not framework itself. So also we support time domain data analysis and also thinking about tools to support spectral analysis with LSDB. So we developed a supplementary package, which is called Nested Pandas, which is an extension of a well-known Pandas package, which helps you to pack your data. So for example, this is one row of the data, so one object, and we have some normal columns like object ID, array, DAC, and then we have item in this row, which would be kind of nested data frame, which would represent the whole spectrum or the whole light curve. When you get it, it looks just a normal pandas data frame, but actually stored in memory and on disk in a very efficient way. So it is very fast to load it and to work with it. I'm showing more examples of this nested format later in demo. So HATS is already used by multiple different archival facilities or considering to be used by some of them. So of course, thank you all IDEX which are working with us, maybe not listing all of them here, including Canadian and Linnea, which is Brazilian. And some individual surveys already put their data and distribute in HATS, for example, S+. Also, we are working with NASA archival facilities. So Space Telescope already provides Pan-STARRS data release 2 data, both metadata and light curves in HATS, which is publicly accessible through the S3 bucket. IPEC is going to provide ZTF data releases in HATS. And we are working with CDS, so on standardization of the format, and when it becomes more stable, hopefully we will have all Vizier catalogs accessible as HATS, which is huge because you could get data from different data facilities. You don't need to download them on your disk. You could stream the data from different places and analyze them together in a single format in a very performant way. Again, in the if you really need to run a large-scale analysis, it would be a nice alternative to, for example, Astra Query plus AstroPy or to TopCat. So talking about Rubin data, we are working with data management team on preparing data preview 1 in HATS. From my understanding, it will not be official format of data preview 1, but we will host it on one of our machines, and IDEX, for example, Canadian data center, will host it for their users. And you could go to this link to see what kind of catalogs we will provide. If you're part of data management, you could find the path on the USDF and could play with the data right now. If not, it is, I'm showing you what you will have with data preview 1. Okay, and I'm going to the demo. Maybe I could take a question while I'm switching screen, if any.
Well, if anyone will ask something, I will let you know. No questions
Okay.
yet?
I will go through them and maybe take some questions after that.
In the end, I will ask it.
Okay. So this is notebook I run on USDF with the current commissioning data. So it is not the final data preview 1, but close to what we will have in the future. So for obvious reasons, I show no real data preview 1 data here. It's being loaded, but I cannot show it, and we cannot do, and as a part, LinkedIn is a part of commissioning team, we cannot use it for science. We can only run verification pipelines with that. So it is basically all the data products we have in HATS. So mirroring all the catalogs plus adding some value-added catalogs. I will show some of them later. So for example, this is just mirroring object catalog or source catalog. Oh my God, the last one, or differential image source catalog. So skip this carry cell. It will not be needed in the future, hopefully. We're working on that. So, and let's load object LC catalog. So what is that? It's object catalog, which is cross-matched with forced source catalog. So for this first source catalog is represented in this nested column inside object catalog. So you have all the rows, so all these, I don't know, 100 or whatever rows from the object catalog. And plus you have this new column, which just packs all forced light curves into this nested representation. And also I computed here one more column, which is just number of sources, which I filter on to select objects having at least 10 sources, or having at least 10 observations. Now I run, so LSDB uses Dask, is Python framework for distributed parallel out of memory compute. So I run task client to just get 5 objects with light curves having at least 10 observations. Here I'm mocking the data, just putting some random numbers, and it is and selecting just 2 columns. So object ID, again, replaced with just 0, 1, 2, 3, and a few columns from forced object force source. So few nested columns. It actually has something like 20 or 30 columns with light curve data. So you see, if we are going to this data frame and just selecting, it's normal, pandas syntax, right? Selecting column and selecting the first element. What we are getting this nested data frame with light curve, which we could plot again, some random data, not real LSST observations, just showing you that the interface of interacting with this nested data is just normal pandas interface, because what you're getting for each object, for each light curve, you are just getting a pandas data frame you could work with. And of course, you could run any user-defined function over this light curve data, right? So you could run any function using all normal columns and nested columns all together to do your science. So we provide very little amount of, built-in functions for analysis, because we believe that community is very diverse and everyone had this, favorite tool. So you could just run any Python code over each of these raw using all this data. Another catalog is differential image analysis objects with light curves. It has 2 nested columns now. So it has differential image analysis sources and differential force sources. They have different dimensionality, right? Because force sources, force sources, you would have a source even if object has very small signal to noise, right? By the definition of force. And again, you could, if you accept them, they would be just normal light curves. And finishing, like to say that we also have a couple of supplementary catalogs with cross matches with ZTF data release 22 and with the Panstars data release 2. Here I'm showing ZTF data. So again, now we have 3 nested columns, so 2 from LSST, 1 from ZTF data release, right? And here I'm just getting the ZTF light curve and plotted. Nothing interesting, but this time real data, because ZTF is public. Okay, I went a little bit out of time, so thank you for your attention.
Thank you. I think considering that we are going to deal a lot with all those huge catalogs, you are doing a good job, as they say. Okay, so questions? Yes, go on, Tamas.
Yeah, thank you very much. Thank you, Kostya, for this talk. It was very interesting and very useful. I just have a question to the method of the cross-matching, because different sky surveys have different instruments, different pixel sizes, different etc. 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 I don't have to tell you this because you know that. But I write codes regarding to cross-matching as well, and I find lots of bricks on the way that and I'm sure that Tim will say lots of useful things as well later in his talk. But what catch my eye that you said that you can cross-match, for example, Gaia with ZTF in just a couple of seconds. How?
So yeah, this is a good question. What I show is, of course, just naive KD tree cross-match. But actually I have forgotten to advertise, we have beautiful incubator program through which you could apply to get 3 months of work with our software engineers and project scientists like myself to improve your code. And we actually had a few interesting projects already mentioned today. So we had Sorka, we had Photod, and actually we worked with Macau. I think it's what Tim will talk about later. So we understand that cross-matching is not a simple problem, but That's why we give you flexible interface to implement your own cross-matching algorithm. And we provide you KD3 cross-match just, as baseline method. Again, we are not aimed to develop any possible analysis upon LSDB in heads. We are aimed to provide you a tool where you could plug your analysis in, right? So, for example, with Markov, we worked on making it possible to load Markov cross-matching results into heads LSDB. So you will be able to use Markov cross matches between, for example, LSST and Gaia or LSST and Wise with LSDB. Or you will be able to implement any, reasonable cross-matching algorithm with LSDB. In most of the cases, KD3 cross-match, maybe with multiple outputs, would be anyway the first step you do. That's why, we provide it as a baseline again. So, this is our current approach, right? So we are happy to work with people working on cross-matching algorithms. We're happy to develop supplementary packages with these people, so you could use them with LSDB, or even include some more general algorithms with LSDB.
How much did you cross-match Gaia DR3 with ZTF?
Yeah, it's basically what I showed. Yeah, so it was Gaia DR3 versus ZTF DR14, but just few columns, right? So coordinates and object ID, something like that.
So not the whole database.
Yeah, again, I did the whole database, but then it took 40 minutes because it basically loads 1 terabyte of data from the disk and puts it back to the disk, and you are just IO bound, right? So if you have faster disks than me, you could do it faster.
Yeah.
If you have slower disks, you will do it slower. So there is no magic, right? So we are limited by the hardware here.
Is it available?
The cross-match result?
Yeah.
I don't think that is available, but first we could talk about it, and second, it's reproducible. So
yeah. Can I drop you a mail about this? Because I would like
yeah,
to
sure. Feel free
check
to
my data as well.
Thank
I
you to write in Slack,
like-
and we have LSD.
I would like to notice both to Tamas and to Kostya, if you guys are going to do this kind of cross matches for the whole data sets, we definitely should discuss within the TVS about making the results of these cross matches available, because yes, it may be reproducible, but if we can do this kind of cross match once and maybe introduce some additional improvements on the quality of the cross match, talking about different methods of cross match, this is definitely that has a huge use for everyone essentially. So
it's true.
I propose to talk about it after Team's talk, because it's part of UK.
Yes, definitely.
And I think that the approach, Macau, for example, approach crowded fields would do it much better job, right? So, but again, happy to help with any approach here.
Well, let's put this thought on hold, and we will discuss it after the next. I think we have left 2 talks, maybe. Let me see. Yes. So thank you, Kostya. We will be back on this topic. And Ryan, I hope that I'm pronouncing your name correctly.
Yeah, that's pretty good.
Okay, close enough. Please go.
All right, thanks, Alex. All right, so yeah, my name is Ryan Lau. I'm a staff astronomer at NORLab, and also on the community science team for Rubin. So I'm going to talk about, and I also put my slides in the chat if you guys want to follow along. And I think, hopefully I'm sharing the right screen. So I'm going to talk about community filters and how we're kind of providing them for the Rubin science community using the Antares broker. So I'll kind of go through that here. Just super high level intro to alerts and brokers. Probably don't need to spend too much time on this with this crowd, but just to kind of set the context. So we kind of all know that Rubin will provide us with detections of billions of stars and galaxies over the 10-year survey. And then every night, millions of transients, variables, and moving objects, which is a lot of stuff. And so it's going to be difficult to sift through these on your own. It's a data set of unprecedented volume and complexity. And so that's the whole purpose of these alerts and brokers, so we can actually ingest them and process them in a meaningful way. So what happens though, when Rubin takes its data, it does this difference image analysis in 60 seconds. So you have a difference image, and whether or not there's something that's varying within 5 sigma, it produces an alert. And these alerts are distributed to brokers that can be analyzed by users. So these alerts will contain, as I mentioned, a 5 sigma difference image source. So whether it's fading or brightening by 5 sigma, and it includes a bunch of data about the that particular object or thing that's changing in time, including astrometry, photometry, light curve history, if that's available, and also some characterization parameters. If you want to look up what's in the alert contents, you can check out the DPDD in that link kind of in the bottom right of this box there. All right, and so what are brokers? We heard about the Think broker from Anais earlier today. So just a quick intro to these. These brokers access Rubin alerts in real time. So these are software systems that ingest, process, and serve these alerts from Rubin and also other surveys to the broader scientific community. The typical functionality includes like watch lists. If there are certain things you're interested in looking for variability or transient activity, you can have those. Predefined or user-defined alert filters, which is what I'll talk about later in this talk, to actually filter down this huge stream of millions of alerts to things that you're particularly interested in that suit your science case. You can also do cross-matching with archival catalogs, some classification. I like to prioritize follow-up, and these are accessible through browser-based user interfaces, as we've seen with the Think broker. Another thing to note too is that the data in this alert packet that's sent, well, the alert itself, so the alert itself is available to everyone. There's a products database, which includes more info, and that's available within 24 hours. That's only accessible to data rights holders, but it can be accessed through the RSP. So another way to kind of access alerts is through this prompt products database. Available now, there's several brokers that are already processing ZTF alerts, so you can check that out. And what we're going to do now is take a look, kind of just a super quick overview of the Antares broker. All right, so Antares is a real-time alert broker. If you go to like antares.norlab.edu, you see the science portal there on the right, where you can kind of explore the latest alerts that have come through. So it's real-time, meaning that so this is all ZTF data now, but as ZTF sends its alerts, it'll start populating on this page. So it allows users to receive, process, and filter alerts from Rubin and other surveys that are hosted there. So as I mentioned, ZTF. And so these alert filters, they run through the data of each alert, and it can produce data on its own based on the properties of the alert, and also provide them with tags and classifications. So if there's something interesting in the alert that matches your science interest, you can have it pass through this filter, and then you'll see all the alerts that pass the criteria that you might be interested in. So you can check the website out, and then also any questions about Antares, you can direct it to antares@norlab.edu. Okay, so in my opinion, the filters are like one of the key things for these alert brokers. So this is an example of an Antares filter. You can actually look at this. The public filters are publicly available. You go to the pipeline page, and under level 2 filters, it shows the publicly available filters that are operating. One of them looks for nuclear transients, so we'll kind of dive into that a little bit. And the point of this filter is to look for alerts that ZTF produces that have occurred close into the nucleus of a galaxy. And then on the right is kind of showing the tags or the alert tag that comes with it. So you can see that there's like 87,000 alerts that have been tagged with this nuclear transient tag, so that have passed through this filter. Here's an example of one of the results from the filter. So you can see it looks like it's working in this case. The alert also comes with the cutouts from the new image. That's kind of this one here, and then a reference image, and then the science image. So that's the difference image. So that what you see on the right is the subtraction of the new image and the reference image, and then the color Simbad image on the left here to show that it does look like we're looking at the center of a galaxy. Okay, so let's take a closer look at this filter. what exactly does this look like, and how do you do this? So you can, it's all done in Python. I think the easiest way to create an Antares filter is to create an account on Azure Data Lab, and then there's like a notebook aspect, and you can load this up in this Antares dev kit. So it's in this Python module. You define it as a class. This one is, let me back, this nuclear transient. And then you essentially just read in the properties that you want from the alert. So these 5 things are what we'll use to filter out the interesting alerts that fall into this category of a nuclear transient. And so just to go into more detail, this is essentially all the code that's running for this filter itself. So here are the properties that I mentioned earlier. So there's a star galaxy score, which gives some sense of whether or not this is more, the thing is more a star or a galaxy. There's the distance from the nearest pan-stars object. There's the magnitude, the ZTF magnitude, so that tells you how bright the thing is, how bright the nearest object is, the distance to the nearest object, and then the IDs of the object IDs and the alert IDs. So this pretty much here is, this if statement is the filter, or the logic that goes into the filter. So it's looking that there's an object close by. I think it's trying to identify if the source is more like a star, I think, or it might be a galaxy. I might be getting that mixed up. And then this, let's see, constraint here to look and to make sure that the fluctuations that you're observing from this alert are significant, that it's not just very low level flux variability compared to the host galaxy. So these are criteria that I think are directly extracted from Sjoerd van Velzen's 2019 paper, section 2.1. And I think he's on this workshop. So if you have questions about it, you can direct it towards him. But I'm also happy to talk about this too. All right, so that brings me to kind of the last point here, which is this roadmap that we have for community alert filters that we're developing on Antares. So Rubin Observatory, in kind of collaboration with the Antares team, will develop these community filters. And what this is a low barrier to entry starting point for the community who want to start doing science with alerts. So we're soliciting feedback on what kind of filters we want for the first set of filters that we want to operate on LSST alerts. We want it to cover a broad range of Rubin science cases, and we expect these to be maintained throughout the entire Rubin operations. So it can be kind of, depending on the complexity of the filter, it can be kind of tricky. So we want this to be like kind of like an entry level examples of how you can write filters for Antares. And let's see. So what else was I going to say about this? Yeah, I guess so. The call is out now. It came out yesterday. Put it out yesterday. So we're looking for inputs on 5 initial community filters. And we posted this on the Rubin community forum. It's just a simple Google form that takes like 5 or 10 minutes to fill out, just to get an idea of what folks would like to see for these first filters. One thing to keep in mind too, this doesn't preclude you going off on your own and creating your own filters. This is just if you want us to help out with providing feedback to create this set of 5 filters, we will do this. But definitely you can go off on your own, create your own user-defined filters for Antares. Yep, so as I mentioned, we put this out yesterday. This QR code goes to the Google form where you can put input on what your science case is, what you'd want to see in this filter. And the deadline is going to be May 30th, so that's about 2 months from now. And we're gonna take this feedback, probably work with the people who submit the feedback to make sure that we develop what they want to see, and then have them implemented around July to September this year, which is approximately when the LSST alerts will begin. Okay, so yeah, with that, I'll end here, and I'm happy to take any questions or if there's any feedback on this process as well. Yeah, it'd be great to hear that. Thanks.
Thank you. Excellent intro and good demonstration of how it's done. And I see right away that there are questions or comments. So Rachel was first. Please go, Rachel.
Hi, thanks, Ryan, for a great talk. I'm looking at the Antares documentation, and what's a lot of the documentation is specific about the properties that it annotates on each alert package and each loci package. What it's saying is actually some properties may be available. And I'm interpreting that to mean that if a specific filter is run, it will annotate the alert with specific properties, which is fine. Does that mean that every filter is always run on every alert so that every alert has those properties? Or if I subscribe to a particular filter's alert stream, then I will get those properties, but not otherwise. Is that the case?
I think yeah, I see what you're saying. I think if the alert matches that filter's properties, then whatever it annotates is added onto that alert. So but I think maybe you could design it in a way where you have your filter run on every single alert and annotate something, but I think that would be discouraged unless it's something that can run super quick. So yeah, my sense of that is if you're looking for a particular type of source and you want to calculate some kind of property of those objects, yeah, you filter down and then you have it annotate what you calculate. Yeah, on that particular alert. If there's someone on the Antares team who's on who can give a better answer than that, then please feel free to chime in. But yeah, that's my sense of it.
Okay, thank you. But there are some properties that are always calculated by Antares itself, if I understand the documentation correctly. Is that true?
Yes, yeah, I believe that's true.
Okay. Thanks very much.
Cool. Thanks for the question.
Thank you. Sjord, do you have a question or comment? And we can still hear you.
Thanks for the nice talk. Yeah, I first have a technical question. So for the community filter, for example, thinking about nuclear transients or tidal disruption events in particular, probably lots of people will want to do their own machine learning based filter. So that's not something that you can really maintain. But then it could still be useful to have some sort of nuclear transient filter that we all agree on, that then downstream people can apply their machine learning on. So then my technical question is, yeah, for these community filters, will you release the result of those as a stream again, as well as a Kafka or Afro stream, such that other brokers again can listen to this, or how do you release the results of these filters?
Yeah, that's a good question. So, right, for these community filters, we would probably want them to be more broadly, more broad than to be a specific focus science case, like machine learning classification of a TDE activity or nuclear transient activity. So, I think, that we could have these operate that you could kind of filter more downstream from these alerts. So, for example, to use this nuclear transient tag, and then user-defined filters can use this to run the more specific code or functions to identify what they're looking at. So I think, yeah, I'm pretty sure it can work that way. I can double check for you on that. But yeah, I think that's our thinking, is that we want to kind of reduce any redundancies of other filters, that if you're trying to do this kind of classification, that you don't need to worry about identifying them first. You can just use these pre-existing community filters that narrow those down for you.
Great. Yeah, that's good. But then by downstream, I hope it's downstream, not just within the Antares framework, but like that you can then also switch to a different broker to do your further filtering on this community stream, or maybe that's not what you have in mind, but that's what I'm trying to get at.
Yeah, that's a good question. I'm not sure off the top of my head what the answer to that is, but like you filter it and then you can have it ingested maybe by another broker, but I'll ask about that.
Okay, thanks. Yeah, let's be in touch.
Yep, thanks, Short.
Thank you. And unless there are any other pressing questions, we are switching to our last speaker of today, 2 hours after it was supposed to happen by the program. I hope I am not ruining everyone's evening. So Tim, are you still around?
Yes, I'm still here.
Fantastic.
Let me see if I can share. Has that worked? No.
Well, we see some awesome picture with a lot of files on your work.
No, that's not right then, is it? Try again. Does that work?
And now we see a half. Okay, now we see the full slide. Yeah, please go on.
Okay, thank you. Right, good. So for those of you who don't know me, I'm Tim Naylor. I work in Exeter in the UK. Most of what I'm going to talk is work that Tom Wilson has done. He's the programmer working on this project, but we've also had help from George Beckett and Mike Reed at the UK DAC and Dominic Sloan Murphy, who has worked on parallelization for us. So the Rubin cross-matching, right? We are part of the UK's in-kind program. We are, as it were, contracted to provide algorithms and software to match legacy catalogs with the Rubin data. We intend at the moment that the matches will be available after every data release and we'll release them through the UK Rubin Science platform. Formally, we're non-directable effort, but actually, practically, of course, we very much welcome input. So the first and obvious question, and people have talked about this already, why is cross-matching hard for Rubin data? What makes Rubin data different? And it was this plot which really brought home to me the size of the problem that we have. And you can see here the cumulative number of sources in an R-band exposure I've marked up single visit here and full depth here. And the two places that I've chosen are L equals 50, B equals 5. So, okay, galactic plane, but quite a way away from the galactic center. And L equals 5, B equals 4 is really in the heart of the galactic center. And you can see here, if you were going to try and match these, in these galactic plane fields with a 2 arc-second radius circle, then even in a single visit, you find there is one source that is not your counterpart in there just because of the density of field stars. And that's in moderate, a relatively moderate region of the plane. Once you go to full depth, then you exceed that here. And the other place to look at is when you get one object per seeing disk. And in fact, if you talk to people who work in crowded fields, a 10th per seeing disk, so down here, is thought of as the disaster. And even if you put the Hubble Deep Field on here, you can see the Hubble Deep Field is getting to the crowded stage. So crowding is a real problem if you are going to want to actually work in the galactic plane. So the question we've asked ourselves is, can we do better? The obvious thing to do is just use a much smaller circle, right? Rather than 2 arcseconds, use 100 milliarcseconds. But actually what you want to do is you want to do the proper probabilistic job, right? Of the probability that your star, find the probability that your star is a field star or the counterpart. And also, as shown in a minute, it's useful to use the magnitudes. But what then hangs you up is you think, okay, so I just take from the Rubin data stream the formal uncertainties in position. Those formal uncertainties do not work in crowded fields because of what I'll describe in a moment, the astrometric tug effect of crowding. Basically, you don't centroid the sources to the right place because of crowding. Also, of course, proper motions in any field will actually muck up your formal uncertainties. So these are basically crowding effects. And what I'm going to talk about is I'm going to talk about WISE, because WISE is a good analog of Rubin in terms of sources per PSF, right? WISE does not go as deep, but has a much worse point spread function, and the crowding is very similar. So it's been what we've done a lot of our work, what we've used for a lot of our work, because it's a good analog. If we can match WISE to get Gaia, we can probably match Rubin to something like Gaia. A nice way of looking at the Bayesian aspect of this problem is to consider these two grayscales here. And what you can imagine is the one on the right is the density of counterparts that you expect to see as a function of magnitude up the y-axis and distance from the position that you think the source should be at on the x-axis. And you can see in this simulation your objects actually cluster here. You expect your counterparts to be close to the position that you're looking at, and you also expect them to be relatively bright, depending on catalog depths, but that's a good assumption in some cases. Whereas your field stars here, you expect no change as you look out to larger and larger radii, but you do expect to see more and more stars as you go fainter. And so you can see this star I've plotted here on both sides. This star is clearly not the counterpart, right? The probability is much higher here that it's for a field star and virtually nothing at that distance from at that distance from the position. This is probably your counterpart, right? It lies here in a relatively sparse region of the field stars, and here, splat bang where you expect the stars to be. For me, the frightening one is this one. This star is clearly not the counterpart. It's just too faint, right? However, if you do a simple circle match, it will pick up this star as being the closest object to the position that you're searching about, simply because of crowding. And that's how the Bayesian match, which can actually improve on what you get. But there are other effects in there as well. And one I've already referred to, which I call the astrometric tug. And this is the fact that as you get very crowded, then what happens is you have other faint stars below your plate limit, which contribute in a sense to the PSF. So to give you an idea of how bad this is, the WISE PSF is 6 arc seconds. A star 4 arc seconds away, 20 times fainter than the source that you're interested in, will disturb your centroiding by 0.2 of an arc second, so 200 milliarc seconds, which is large compared with the formal uncertainties. And what we're thinking about here, just to put it in context, is this is your Gaia position. This is your true WISE position. And then your WISE position gets perturbed slightly out here by some other WISE source way over here in your PSF. And that makes it mean that your uncertainties that you get from straightforward centroiding are not the ones that you have to use for a Bayesian match. And this again rams home the point about what's happening in the crowding. This is if a field from WISE, and if you just took the WISE uncertainties, then you would expect the distribution of counterparts to look like this, right? To the distribution of the distribution of WISE sources. But because of this effect of the astrometric tug, what you actually find is this point here. And you can model it. You can model it beautifully, right? Because you know from galactic models what you expect the crowding to be. And if you do that, that is where Tom's prediction for what the distribution of counterparts would look like. And there are no free parameters in that model. So it works really remarkably well. So what's the current status? We believe that what we're doing now is a huge technical leap beyond circle matching, and it's absolutely vital in our galactic plane fields if you're going to get your matching right. To give you an idea, if you get 10% of your matches wrong, which you can easily do by the time you've got 1/10 of a field star per circle that you're searching, 10% is completely unacceptable as a mismatch rate if you're looking for rare objects. You will find things which look interesting simply because they are matching the wrong sources. The crowding effects on the astrometric uncertainties I've talked about, and this also is crucial, using the magnitude information to actually help you find matches that you would not find purely on the astrometric information. So far, we've done WISE and Gaia, and we've made that available on the RSP. Now, it's not actually the best, well, it probably is the world's best match, right? But we know there are flaws in it, but those are almost cured. We've done Hyper Supreme Cam as something similar to Rubin versus Gaia. And we've also, as part of commissioning, we've worked on operational rehearsal data for reasons, because as you can imagine, this is important for commissioning, because if you're going to try to assess how good your positions really are, you have to know these other things that disturb your positioning. In progress, we've got a Vista and 2Match, and as I say, support for commissioning. We also have some software, which we call the SuperMatch software, which allows you to bring many catalogs together and with those so that you can take one Rubin source and look at what its cross matches in Vista, 2Match, WISE, etc. So what you get out of this software, right, is you get 3 tables per cross match. You get a merged catalog data set, which is the matches, and then 2 non-match data sets. It's a relatively thin table because we don't want to copy across all the information from the other surveys. So you'll get the designations of the sources, you'll get the RA index, or perhaps the longitude and latitude of the sources, and the magnitudes in all the bands for all the objects. The most important thing that we add is the match probability, so how likely it is that 2 sources match. There are 2 other things that you can look at. You can look at an astrometric likelihood ratio, which is just based on the position on the astrometry, and a photometric likelihood based on the magnitudes. But also, because we calculate these contamination rates, because we need them, we can give you to them. So we can work out what the average contamination of a source is, so how much brighter it is because of the things hiding in the PSF. And we also present the average contamination and the probability of having a blended contaminant of above 1% of the flux. Actually, we provide 2 match runs per catalog pair, one which has the astrometric information, which has the photometric information used, and one that doesn't, because we think there will be times when you're looking for such peculiar objects that you don't want to actually use you don't want to use the colors. And all this is wrapped up in Tom's package Macau, which people have already referred to. So the future, an improvement, we have a statistical proper motion algorithm, which looks at whether or not just looks on the face value of the magnitude, what you might expect the proper motion to be. We also want science validation done. We're doing some of that ourselves, but we would like volunteers. If you have a scientific need at the moment to have 2 catalogs cross-matched, and especially if they're crowded, then please come and ask us, and we'll see if we can put that in, and then you could give us scientific validation. So that's all I wanted to say. Thank you.
Thank you. Another extremely important topic, and it's said that we are so much behind the time. I feel like we are already tired while there are so many important things to discuss. But so far, questions? Yes, please, Sarah.
Yes, just to comment that I think that our team will contact you because we are strongly interested in that. So as a test case of a crowded field photometry and external data sets for young stars and star forming region, this will be crucial. Yeah.
Yeah, please do, Sarah. That would be good.
Yeah, you already know that we are interested in the.
Yeah.
So yeah. Just to emphasize this, I think that also in TVS, in the crowded field photometry task force, there would be other potentially interested people as well.
Okay, thank you. Any other questions? Okay, so I will probably refer from the questions because I'm already a little bit tired and I'm not sure that I can properly formulate it. If I think about it later, I will send it via Slack. So thank you. With this, we are finished with our scheduled talk. And we are significantly behind the schedule. So first of all, thank you everyone, the speakers and the attendees for presenting their work and contributing to the discussion. It was all extremely useful and interesting, and we are pretty close to things getting really heated in the next few months. So the question is, can we still dedicate at least half an hour to the discussion of the current topics? Because we definitely wanted to discuss the period determination algorithms and possibility of coordinating them. We definitely, I think, wanted to discuss something about classification, and then there is another topic with cross-match. So do you still have the energy to discuss this a little bit?
Of course, we are full with energy.
Okay, Tamas is very enthusiastic. So I'm not going to hold everyone here who is already tired, because I understand that everyone is in different time zone, and probably maybe someone has other things scheduled. Not really, Dragana. Yes, I understand you. But still, let's stay for a little bit. And those of us who still has energy. And let's figure out whether there are some important things that we can do collectively regarding these topics of period determination, classification. I think we also scheduled something about the community filters and so on, but most of the people from brokers have left. Yes. So I will probably open the floor with the topic of period determination. So Tamas already told that he and his team would like to try several other algorithms for different science cases. I would like to hear from other people. Do you have some science cases for which you think some specific period finding algorithms are needed? And what are the problems with those algorithms? Are they computationally expensive? Are they not implemented in a convenient form? Dramatic silence.
Okay, I maybe will start with something. So what I think will be challenging with, and we partially covered it already with Lomskargel, for example, for Rubin data, is that multi-band approaches are all a bit different. They, if you need phase shift, right? So for example, if you know that your object changing color, they computationally expensive, you must go, you cannot go with fast Lomskargel, you must go with slow implementation. And also, even if you use a multi-band implementation from AstroPy or from somewhere else, there is still a problem that if you are doing it for multiple bands and one band is very noisy, I'm looking at a U band, it should become redder because you should be shy how noisy it is usually. So, you know, adding all bands could make it worse than, you know, using just a single band or a couple of bands, because some bands could be just very noisy for particular type of objects. Do you have experience with that? Do you think there is a good strategy with that?
So by us, for example, we would like to sorry, we are aware of this problem, and this is why we would like to try it out. The problem is that obviously there is no comparable dataset to LSST right now. There are some, like ZTF, which are very useful, but they don't contain, for example, U-band or Y-band or etc. But it's very useful. I hope that maybe this would be very useful for us as well, if the I-band data will be accessible in ZTF. Because there we could make some experience in 3 bands. Most of our stars are only presented in G and R. So 2 bands are not so good in this experiment.
Out of curiosity, is it possible to prepare a synthetic data set for testing this thing? So just take model light curves, try to see them with LSST cadence and test different algorithms on them?
I think the cadence is not a problem. I think the synthetic data is the problem, because there are no actual good working models to just make synthetic data, for example, a classical SFA star. And we don't even have models for example, U-band.
I do agree. So we have Elastic, but unfortunately I'm responsible on creating RL-Lyra and Delta Scuti models for Elastic, and I didn't do a good job on U-band because I just didn't have,
but there are no
SAD model. Yeah, so I didn't have SAD model, so I basically just used ZTF data and extrapolated it, which couldn't work well.
As for someone who's outside of this topic, why doesn't it work well? What is the problem?
Lyman break or Balmer break, one of them.
Right.
Yeah, so you have very different spectra. So U-band is much fainter than just a naive, for example, black box approximation or something
So
like that.
essentially, we are talking about the fact that we do not know which period finding algorithms will be good for multi-band observations of the types of the objects that were never observed in these bands before, essentially.
Yeah, that's true. I think we can make some parts of it in OGLA or in ZTF or etc., but nothing is close to what LSST will have.
So apparently in the beginning, we will have to mostly rely on stuff that we tested on the other bands, so grids, and then we will add the U-band later to our algorithms.
I think, honestly, I was very, very, very much stressed by this topic lately. But after that, when I realized that after the first data release, most of our stars will be not good for any scientific thing, because we cannot produce any meaningful light curves from them. I just switched, and then Robert, he already left, he agrees with me that, okay, then have a bunch of stars with 6 filters and then just run experiments and see if our previously made methods will work or not. But I'm sure that we will try to do something with existing data like ZTF, and just okay, we will have not a couple of 100,000 stars, just a couple of thousand or tens of thousands, but maybe there is a good way to collect stars with available 3 filter data and then make something useful from it and make the data much more sparse, less ST-like.
Well, synthetically, artificially downgrading them and testing this kind of thing. So it is mostly not the question of not having the right algorithms, because there is it seems like the obvious first choice of testing is multi-band Lomskargol, but it's mostly a question that we do not have a good data to test whether it will perform well, right?
The problem with LSS data, I think that the data is very sparse. And it's very sparse in the first 1 or 2 data releases. So we will have just a couple of points per filter. And this is why we try to do something different to be able to utilize all 6 filters, or 4 or 5. And just coming from the back and some kind of autocorrelation or something.
And what about that field that will be observed to the 10 years depth or 20 years depth in the first year of observation? Is it going to be observed with higher cadence? Can we somehow use that data? So I remember, I'm not sure whether someone can reference it better than me. So in the first year, there will be a small patch of sky. I probably can find it somewhere on the slides. That will be observed to the full survey time depth in the first year. So I suppose that there will be enough number of observations to produce quite well-defined light curves, obviously for short period objects only, but it would be pretty good, no?
We will have some, at least chiral error even in DP1. So we absolutely could start some validation with DP1.
Yes, but I was talking, okay, if I will find the reference to this field, I will put it in the chat because I'm afraid that I will confuse you with some incorrect information. Okay, so I feel like everyone is a bit dazed after a few hours of workshop. Is it a good idea to try to hear anyone's thoughts on classification, or is it better that I will just wrap it up and say, have a nice evening, everyone? Five, four, Tamas?
Wrap it up.
Wrap it up. Okay. Decisive decision. Okay, Angelka, were you trying to say something? Probably
Perhaps
support.
thank you to you, Alex, for hosting us tonight.
Yes,
This was,
yes, and let us go, Alex. Okay, I see you. I hear you. Okay, thank you everyone who came and stay. Have a nice evening, rest of the day, whatever it is in your place. I will publish the recording in a few days, and maybe if there are some notes from our AI companion, I have no idea what is the quality, I will publish it as well in the TVS channel. Thanks for showing up, thanks for excellent talks, and see you sometime in the next meetings.
See you.
Thanks very
Last
much.
minute
Bye-bye.
question, do we share slides somewhere?
Yes, I suggest that we are doing it voluntarily in the channel that I sent in the email. It's probably the easiest.
Okay.
So everyone who wants
TVS
to, yes,
Software Workshop.
yes, I will.
Okay.
I
Thank you so
will
much.
put the reminder to the TVS channel. Okay,
Thank you so much.
Okay.
Thank
Thank you.
Bye.
And if you can provide an overview of this at the TVS general meeting.
Absolutely.
Yeah. Thank you very
Sure.
much.
Thank you. See you. Bye.